Hello there and welcome to Life Beyond Seen, where curiosity gets cozy and long questions are given room to breathe. Tonight we are heading toward a river that has earned a strange reputation among researchers, not because it is cursed, not because it is mythical, not because someone saw glowing eyes in the fog and decided to retire on the spot. Nothing quite so dramatic. The real reason is much more unsettling. The Congo River is one of those places where science arrives prepared, serious, well-equipped, and then slowly realizes the river has no interest in being easy. Before we settle in, I would love for you to take a quiet second and think about where you're listening from right now. What country? What city? What room? What little patch of night or morning has brought you here? And what time is it where you are? It feels fitting somehow that while you listen to this, people elsewhere are eating breakfast, missing trains, washing dishes, or pretending they are definitely going to bed after just one more video. If this kind of slow journey helps you unwind, or if you simply enjoy having your curiosity gently escorted into strange territory, do like the video, subscribe, and spend a little more time here with me. It helps this calm corner find the people who need it. And now, let's ease into it. The Congo River sounds, at first, like the kind of subject you might file under geography. Important, certainly. Large, undeniably. But still, a river. Something to locate on a map, underline in blue and move on from. Then you start reading about it. Then you look into what hydrologists, biologists, geologists and field researchers have actually said about working there. Then you find out that this river is not merely large. It is colossal, physically aggressive, unusually difficult to measure, and in places so deep and so violent that it creates conditions more often compared to ocean trenches, underwater canyons, and biological isolation chambers than to the usual idea of a freshwater river. At that point, the phrase "terrifies scientists" stops sounding like clickbait and starts sounding like a slightly theatrical way of saying, this place has a habit of humbling people with advanced degrees. The Congo River runs about 2,900 miles, or roughly 4,700 kilometers, making it Africa's second longest river after the Nile. In terms of water volume, it is one of the great river systems on Earth, carrying an average flow of about 41,000 cubic meters per second at its mouth. That is an absurd amount of water, the kind of number that sounds tidy on paper and completely unreasonable in motion. It drains a vast portion of Central Africa and feeds one of the largest rainforest regions on the planet. This is not a decorative ribbon of water wandering politely through the landscape. This is a system with reach, force, and consequences. It shapes transport, ecology, local life, and climate across an immense basin. Even before you get to the most dangerous stretches, the scale alone tells you that this is a river capable of setting the terms of engagement. Humans do not really boss rivers around at this scale. We negotiate with them, usually badly, and often after they have already made their opinion known. And yet the Congo's most unnerving qualities are not simply about size. Plenty of rivers are long, plenty are powerful. What makes the Congo especially unsettling to researchers is that some of its most extreme behaviour is concentrated in its lower reaches, where the river narrows, plunges, accelerates, folds over itself, and becomes astonishingly difficult to read from the surface. The lower Congo includes a series of falls, rapids, and steep drops as the river makes its way toward the Atlantic. According to USGS work on the lower Congo, this reach includes 66 falls and rapids and drops roughly 270 meters over about 498 kilometers. In some measured sections, scientists found highly energetic flow, full-depth turbulence, and depth-averaged velocities exceeding 4 meters per second. That does not merely mean fast water. It means water powerful enough to complicate navigation, disrupt measurements, and create a world below the surface that is far more segmented and hostile than a casual glance from the bank would suggest. This is where the Congo begins to feel less like a river in the usual sense and more like a machine with too many hidden moving parts. One of the things that has fascinated scientists for years is that the Lower Congo is widely regarded as the deepest river in the world. Measurements and fieldwork have reported depths of around 220 metres in places, or more than 700 feet. That is deep enough to change the entire character of the water column. Light penetration becomes severely limited. Pressure changes. Currents can behave in ways that are extremely difficult to observe directly. Fish populations can become separated not by land, but by the river itself, by invisible hydraulic barriers strong enough to isolate one zone from another. In many people's minds, rivers divide places horizontally. The Congo also divides vertically. It creates stacked worlds: surface, mid-water, deep channel, plunge zones, side eddies, vast corridors, calmer margins. It is less like one simple flowing body and more like several overlapping environments, all occupying the same address and refusing to introduce themselves properly. That vertical complexity is one reason the Congo has become so important to evolutionary biology. In the Lower Congo, scientists have documented more than 300 fish species, many of them highly localized or found nowhere else. Researchers at the American Museum of Natural History and others have argued that the river's intense currents act like walls of water, separating fish populations even across relatively short distances. In ordinary terms, two fish may be living in what looks to us like the same river, perhaps not even terribly far apart, and yet the hydraulic conditions between them are so extreme that breeding across those barriers becomes unlikely or impossible. Over time, separation leads to divergence. New traits emerge. New species appear. Some fish from the Lower Congo show unusual adaptations linked to darkness and depth, including reduced pigmentation and severe eye reduction, as in the blind cichlid Lamprologus lethops. That is the kind of thing that grabs a scientist by the shoulders. It means the river is not just carrying life through a landscape, it is actively engineering evolutionary isolation in real time. Now, there is something quietly unnerving about that. Not in a monster-under-the-bed sense, in a more serious way. Science likes systems it can model, or at least approach with confidence. You can study a forest canopy, a coral reef, a glacier, a desert basin. They may be difficult, but the basic architecture is visible. The Lower Congo, by contrast, hides much of its architecture beneath opaque, forceful, fast-moving water. Researchers can sample it, map parts of it, lower instruments into it, and build more refined hydraulic models, but the river still has a tendency to remind them that observation and control are not the same thing. A depth measurement is not the same as understanding the full dynamics of a channel. A velocity reading is not the same as making the place predictable, and a map, however precise, can still fail to capture how dangerous it feels to work in an environment where the water itself is constantly generating complexity. There is a difference between knowing a fact and knowing a force. The Congo often grants scientists the first and withholds the second until they are already in the boat. It also matters that the Congo Basin has long been understudied relative to its global importance. Official summaries from the Royal Society's Congo River Research Initiatives note that decades of war have left the region among the least studied in the world, even as the river remains essential for transport and central to the lives of millions in a basin with limited road infrastructure. That gap in knowledge is not just an academic issue. It means scientists have been trying to understand one of Earth's greatest river systems with incomplete data, limited historical access, and all the practical difficulties that come with working in a huge and logistically demanding environment. So when people say the Congo still terrifies scientists, part of what they mean is this. Even now, in an age of satellites, remote sensing, computational models, and portable measurement tools, there are still major basic questions about this basin that remain hard to answer. And when a river stays ahead of your methods for that long, you begin to respect it in a very sober way. There is another layer to this, and it is worth lingering on because it gives the Congo a kind of scale that is easy to miss if you only think about the surface river. The Congo does not stop being dynamic when it reaches the sea. Research published in Nature has shown that sediment flows linked to the Congo River mouth can generate turbidity currents travelling more than 1,130 kilometres through the submarine Congo Canyon and deep sea channel system, accelerating as they go. In other words, the river's influence continues far offshore in a connected system that links continental water flow to deep marine processes. That is extraordinary. It means the Congo is not only a difficult freshwater system, it is part of a larger conveyor of energy and sediment extending into the Atlantic in ways that are still being actively studied. A river that continues rearranging the seafloor far out to sea is not merely scenic. It is a force with a long memory and a very wide reach. This helps explain why scientists tend to speak about the Congo with a mix of excitement and caution. Excitement, because it is one of the richest natural laboratories on Earth for studying hydrodynamics, speciation, freshwater ecology, sediment transport, and river evolution. Caution, because it is also a place where assumptions fail. Calm-looking surface water may conceal a deep hydraulic boundary. A relatively short stretch of river may separate organisms more effectively than an obvious physical barrier on land. A system that appears surveyed may still be poorly understood in function. And the practical act of studying it can involve dangerous navigation, difficult logistics, extreme currents, and the constant possibility that the part you have not yet measured is the part that matters most. Scientists are not frightened because they believe the Congo is supernatural. They are frightened, or perhaps more accurately unsettled, because the river demonstrates how much complexity can hide inside something we think we already understand. It turns river from a familiar noun into a warning that familiar nouns are not always simple. And I think that is part of why this subject grabs people so quickly. A mountain looks intimidating. A volcano advertises danger rather clearly. Even a storm has the decency to arrive with dark clouds and some advance notice. But a river often feels knowable. People fish in rivers, cross rivers, name cities after rivers, build histories around them. Rivers are usually taught to us very early, right alongside lakes and hills and forests, as manageable features of the world. The Congo quietly refuses that simplification. It is a river that behaves, in places, like a set of hidden chambers connected by violent motion. It is a river that can isolate species, defeat neat surface readings, challenge fieldwork, and remain partially mysterious even after years of serious study. It is familiar in category and alien in behaviour. That combination tends to bother us more than obvious danger does. The obvious threat is easier to file away. The thing that looks ordinary and behaves like an exception is what stays in the mind. So when we say the Congo River still terrifies scientists, what we really mean is that it keeps exposing the limits of comfort. It is too deep in places for light to do much good, too forceful in places for easy movement, too hydraulically complex for a quick glance to tell the truth, too biologically strange to be dismissed as just another big river, and too important, frankly, to ignore. It matters to hydrology, to ecology, to the people who depend on it, to the broader Congo basin, and even to what happens where river and ocean meet. It is both a lifeline and a puzzle, a practical route and a scientific provocation. A river can be all those things at once. The Congo seems determined to prove it, and that is where we need to begin, because before we get to the blind fish, the underwater walls of current, the black depths, and the measurements that made seasoned researchers rethink what a river can be, we need to place this giant properly on the map and understand how a waterway in the heart of Africa became one of the most physically intimidating freshwater systems on Earth. Once you see where it runs, how it gathers its strength, and why the lower reaches become so extreme, the fear starts to make a very practical kind of sense. To make sense of why the Congo can unsettle serious researchers, It helps to step back before stepping in. The fear does not begin with the deepest trench or the fastest current. It begins with scale. The Congo River is not a narrow line on a school atlas doing its best to behave. It is Africa's second longest river at about 2,900 miles, or 4,700 kilometres, and its drainage basin covers roughly 1.335 million square miles, or 3.457 million square kilometres. It rises in the highlands of northeastern Zambia as the Chambashi River, and then sweeps in a giant counterclockwise arc, turning northwest, west, and southwest until it reaches the Atlantic Ocean. Even that basic outline tells you something important. This is not a local waterway with a local personality. It is a continental system, broad enough and long enough to shape roads, trade, climate, settlement, and daily life across a huge portion of Central Africa. When people call it a giant, they're not being dramatic, they're being accurate. The basin takes in almost the entire territory of the Democratic Republic of the Congo, as well as most of the Republic of the Congo, the Central African Republic, eastern Zambia, northern Angola, and parts of Cameroon and Tanzania. That means the river is not simply in the heart of Africa in the casual sense. It's tied directly to the geography of multiple countries, multiple climates, multiple ecosystems, and multiple human histories at once. It also means the Congo is one of those rivers that becomes harder to describe the longer you look at it. Is it a river system, a transport network, a forest engine, a lifeline, a border, a corridor, a barrier, a source of food, a source of power, a scientific problem, or a daily necessity for millions of people? The annoying answer, from the point of view of anyone who likes clean categories, is yes. It is all of them. Rivers this large do not cooperate with tidy labels. They collect responsibilities as they move. One reason the Congo holds its size so convincingly is that it sits in an equatorial region where rainfall is heavy throughout all or almost all of the year. Britannica notes that upstream from Malibbo Pool, the basin receives an average of about 60 inches, or 1,500 millimetres, of rain annually, and more than 1/4 of that water is discharged into the Atlantic. That steady hydrological input matters. It helps explain why the Congo's flow is so powerful and so persistent. At its mouth, the river discharges around 41,000 cubic metres of water per second. That number can feel a little lifeless until you remember what it means in practice. It means movement on a scale that wears landscapes down, carries enormous sediment loads, feeds wetlands and channels far from the point of origin, and keeps the river from behaving like a seasonal trickle that politely disappears when things get dry. The Congo has wet seasons somewhere in its basin almost all the time, which gives it a kind of continuity that is impressive on paper and intimidating in the field. Its shape matters too, because the river's course bends in that large counterclockwise arc, gathering and redistributing water across a vast interior. The Congo is not just long, it is structurally central. It reaches into the middle of the continent and binds together areas that might otherwise seem separate. This is why the river has long mattered as a route as much as a feature. With its tributaries, the Congo forms the continent's largest network of navigable waterways. That phrase can sound pleasant, almost leisurely, as though one is picturing a relaxed boat ride, and perhaps someone in a hat with excellent local knowledge. And in some reaches, the river does serve exactly that practical role. But the same sentence comes with an immediate warning attached. Navigation is limited by 32 cataracts in the lower course, including Inga Falls, and those cataracts make the river unnavigable between Matadi and Malibbo Pool. So the Congo is both connector and interrupter. It offers one of Africa's most important inland water networks, then casually inserts a section that says, in effect, no, not here, absolutely not here. That mix of usefulness and refusal is part of the river's character all the way through. In its broader middle and upper reaches, the Congo can appear generous, even accommodating. It supports transport where roads are limited. It links communities. It carries people, goods, and local economies through terrain that would otherwise be far harder to cross. Royal Society researchers describe the river as essential for transportation in a basin where road infrastructure is limited, and they also note that the Congo remains one of the least studied major rivers in the world in terms of hydrology and hydrodynamics. That combination says a great deal. Millions depend on it. Scientists still do not fully understand it. Those two truths sit side by side. One gives the river social importance, the other gives it scientific weight. Together, they explain why the Congo is not merely famous, it is necessary and not yet fully known, which is a very uncomfortable combination if you happen to be the sort of person whose job involves saying, with confidence, how a major river behaves. And around that river sits one of the most important forest systems on Earth. The Congo Basin contains the world's second largest tropical rainforest, surpassed only by the Amazon. NASA describes it as spanning 6 countries and about 3.7 million square kilometres, while WWF emphasises its extraordinary biodiversity and the role its forests play in storing carbon. This matters because the river cannot really be separated from the forest that surrounds and feeds it. The river is not a blue thread dropped onto a green background for decoration. The forest and the river operate as parts of the same regional system. Water shapes the forest shapes the water cycle. Floodplains, swamps, tributaries, seasonal patterns, and vegetation all contribute to the basin's larger rhythm. When scientists look at the Congo, they are not only studying a channel of moving water, they are looking at a massive living system in which freshwater dynamics, forest cover, wildlife, carbon storage, and human livelihoods overlap. That makes the river more significant than its own banks suggest. It also makes mistakes more expensive. The human side of this is easy to understate if you only focus on maps. WWF notes that the regional population across the 6 Congo Basin countries is over 157 million people, with some 60 million relying directly on the forest for food, medicine, materials and shelter. The river's role here is not symbolic, it is practical. It helps move people and goods, it supports fisheries, it links settlements that would otherwise be difficult to reach. It influences agriculture, local trade, and the basic logistics of living in a basin where dense forest and limited infrastructure change what is easy and what is hard. This is part of what makes the Congo different from the sort of landscape people only visit as observers. Many river systems are scientifically interesting. The Congo is scientifically important while also being deeply woven into ordinary life. Ferries, pirogues, cargo boats, local crossings, markets, fishing, border movement, and riverbank communities all sit within the same system that hydrologists describe in terms of discharge, depth, and energy. The river does not separate the human story from the physical one. It keeps forcing them together. There is also the simple visual fact that the Congo occupies the centre of the continent in a way that feels almost strategic. If you look at the basin on a map, it does not merely pass through the heart of Africa. It spreads through it, gathering tributaries and influence as it goes. The remote headwaters begin far from the Atlantic, and the full system pulls water from a huge interior before sending it westward to the coast. Britannica notes that the source lies only about 430 miles, or 700 kilometres, from the Indian Ocean as the crow flies, even though the water itself travels across the continent to the Atlantic. That is the kind of geographic detail that makes you pause. The river could have been part of one coastal logic, but instead it belongs to another. It crosses distance and topography in a way that reinforces how large the continental interior really is. For people living along it, this is not a novelty fact. It is the reason the river matters. For scientists, it is another reminder that the Congo is not a minor branch of some simpler system. It is one of the defining arteries of Central Africa. Then there is Malibbo Pool, which deserves attention because it shows how the Congo can switch moods without changing identity. Britannica describes Malibbo Pool as a lake-like expansion of the lower Congo, covering about 174 square miles or 450 square kilometres, divided into deep navigable channels by Bamu Island. Kinshasa and Brazzaville sit on opposite banks there, facing one another across the same widening of the same river. That image matters because it shows the Congo in one of its more readable forms. Broad water, urban life, channel traffic, political capitals, inland navigation. It almost looks manageable. It almost looks like the river has agreed to be useful and legible at the same time. But just downstream, the mood changes. The lower course drops hard through rapids and cataracts toward the Atlantic, so Malibbo Pool works almost like a hinge. Above it lies a huge inland waterway system that people can use. Below it, the river begins showing why so many measurements, expeditions and plans have to be made with a great deal of respect and often with a slightly tense expression. That shift from broad route to violent descent is one of the most important things to understand about the Congo as a whole. The river in the interior can be wide, winding and central to transport. The lower river becomes something else. USGS describes the lower Congo as one of the deepest and most powerful stretches of river on Earth, dropping about 270 metres from Malibbo Pool through the gorges of the Crystal Mountains to the Atlantic over 498 kilometres. Britannica's summary of Livingstone Falls adds that the lower course includes a series of 32 rapids and cataracts, extending roughly 220 miles between Kinshasa and Matadi, with a total drop of about 850 feet, or 260 metres. Those numbers are not simply dramatic decorations. They explain why the Congo can function like several rivers under one name. In one stretch, it is a route through the interior. In another, it becomes a descending hydraulic obstacle course with bedrock control, constrictions, deep pools, and energy levels that make surface impressions dangerously incomplete. This is also where the phrase, giant in the heart of Africa, becomes more useful than it first sounds. A giant is not just something big. A giant changes the behaviour of everything around it. The Congo shapes settlement. It shapes trade. It shapes ecology. It shapes what species can live where. It shapes where research is easy, where it is risky, and where it remains frustratingly incomplete. It supports one of the world's great rainforests, influences one of the world's great freshwater systems, and serves millions of people while still resisting neat scientific closure. Royal Society work and other hydrology reviews have emphasised that the basin remains understudied relative to its size and importance. That understudy is not because the river is unimportant. It is because the scale, logistics, conflict history, and sheer complexity of the system have made deep understanding harder to build than many outsiders assume. The Congo is not obscure because it lacks significance. It is difficult because its significance is enormous. So by the time we arrive at the lower reaches, the point is not that the river suddenly becomes impressive. It has been impressive for thousands of kilometres already. What changes is the way that impressiveness expresses itself. Upstream, the Congo announces size, reach and dependence. Downstream, it begins to announce force. Upstream, people live with it as a root and resource. Downstream, researchers confront it as a problem that refuses to flatten itself into something easily measured. That difference matters because it keeps us from making a common mistake. The dangerous part is not dangerous because it is separate from the rest of the river. It is dangerous because it is the concentrated expression of everything the larger system has been gathering all along: water volume, gradient, channel confinement, hidden depth, and power. Once all of that is squeezed into narrower, steeper reaches, the Congo stops sounding like geography homework and starts sounding like a very serious field briefing. And even from high above, with the map laid out neatly and the labels behaving themselves, the river can still mislead you. It can look broad, patient, and almost calm in places. It can look like a feature you understand because you know where it starts, where it bends, and where it ends. But the Congo has a habit of making that confidence feel premature. The scale of the basin, the dependence of millions of people, the reach of the forest, the navigable stretches, the sudden breaks in navigability and the violent lower descent all belong to the same system. That is the point to carry forward. It is one river, but not one simple experience. And once the surface begins looking calmer than the water below has any right to be, the next step is to look at what that surface has been hiding. From a distance, the Congo can look almost reasonable. That is part of the problem. On a map, it presents itself as a long, dark path through Central Africa, wide in places, neatly outlined, almost as if the continent had taken a pen and drawn a route through the forest. From satellite views, the main stem can appear broad and composed, and in some stretches the river is so wide that the skies above it are noticeably clearer than those over the surrounding forest. NASA has noted that parts of the Congo can be up to 5 kilometers wide enough to affect cloud formation, because the water and the air above it are cooler than the humid forest around it. So from above, what you often see is a clean, open band through dense green. It does not look like a place that should be hiding some of the most complex freshwater hydraulics on Earth. It looks, at first glance, like a river that has agreed to be visible. That first glance is misleading in a very specific way. The aerial view tells you where the water is, how wide it seems, how it bends, and how it occupies the landscape. It does not tell you what the river is doing beneath the surface, and in the Congo that difference matters more than most people realise. A 2019 field and satellite study of the Congo's main stem made the limitation plain. Satellite measurements are useful, but they are limited by resolution, coverage, uncertainty, and their inability to directly measure bathymetry or discharge. In other words, from above you can see the skin of the river. You cannot see the shape of its floor, the arrangement of its deep channels, or the exact behaviour of the water moving through them. You are looking at the visible part of a much larger machine. That is fine if you are appreciating geography. It is much less fine if you're trying to understand a system that can hide major hydraulic changes in places that do not look especially dramatic from overhead. This gap between appearance and reality became especially important when biologists working on lower Congo fish started asking a simple question with very inconvenient consequences. Why were so many fish populations in the same river behaving as though they were separated by walls? Why were species evolving in small pockets, with local forms and unusual traits, in what seemed from the surface to be a single connected waterway? As the American Museum of Natural History later explained, researchers eventually realised they had been looking at the river too much as humans look at a river, from the bank, from the boat, from the map, and not enough as a fish would experience it. Once they began pairing biological work with hydrological measurements, the picture changed quickly. The lower Congo was not a single open corridor of water. It was a broken, forceful set of deep channels, velocity cores, upwelling zones, and hydraulic separations that made the river far more fragmented below the surface than it looked above it, and the river does not advertise that truth very generously. Plenty of dangerous landscapes do you the courtesy of looking dangerous. A cliff usually appears to be a cliff. A waterfall tends to introduce itself before you accidentally build a picnic next to it. The Congo often behaves differently. In some reaches, especially when seen from above, the water can look broad, dark and steady. Even where rapids are present, the full scale of what sits underneath is easy to underestimate. USGS work on the lower Congo describes a stretch dropping about 270 metres from Malibbo Pool through the gorges of the Crystal Mountains to the Atlantic over roughly 498 kilometres, a descent filled with rapids, cataracts, and deep pools. That already sounds serious. But the more unsettling detail is that much of this lower reach remained a hydraulic mystery even to specialists, despite being one of the deepest, most powerful, and most biologically diverse river stretches on Earth. The river could be looked at, crossed in places, used, photographed, and still not be properly read. What makes this especially deceptive is that the surface is not a reliable guide to the structure underneath. In the Bulu reach of the lower Congo, USGS researchers found that turbulent and secondary flow structures, can span the full depth of the flow, up to 165 metres in that reach, while depth average velocities in some high shear zones can exceed 4 metres per second. Those are not shallow ripples and ordinary cross currents. Those are deep, powerful flow structures operating through a massive water column. A person looking from above may notice movement, perhaps some visible force, but not the full architecture of it. The river does not conveniently outline its internal lanes and barriers on the surface like a highway map. It does not mark the places where a deep pool drops hard into a constriction, or where a hidden jet of fast water cuts between calmer margins. The surface may look busy, or it may look merely swift, while below it the water is already reorganizing itself into something more like separate internal worlds. That is one reason the lower Congo has been described in terms that usually belong to landforms, not rivers. Researchers talk about plunge pools, gorges, constrictions, and bedrock control. They describe hydraulic environments that isolate fish populations, even when those populations live within hundreds of meters of one another. In the Bulu Reach, the USGS team found no coherent bank-to-bank cross-channel flow structures. Instead, regions of flow separation near the banks were isolated from one another and from the opposite bank by high shear, high velocity zones. Later in the paper, the researchers explain that low flow recirculation zones near the banks are pinched off by swift downstream flow, occupying almost the entire cross-section. So a calmer looking edge does not necessarily mean an easy path across the river, or even an easy path to another calm looking edge. The centre can function like a hydraulic wall. From above, that is almost impossible to appreciate properly. The river still looks continuous. The organisms inside it may experience it as partitioned, even collecting the data to prove this was not straightforward. The field teams were not gliding through a tame, survey environment with perfect communication and predictable water. The USGS account of the Bulu work notes that the remoteness of the survey sites and the lack of navigable water in the lower Congo required local boats and operators. The primary craft was a traditional pirogue, a hollowed-out log fitted with a small outboard motor. The researchers say the swift and often turbulent flow, combined with limited communication with the operators, made it difficult to remain on course for repeated transects. That detail matters because it reminds you that this is not just a conceptual difficulty. The calmness from above is misleading in practical ways too. The river may look mappable from an aerial image, but obtaining repeated measurements in the real channel means entering a place where the water resists straight lines, instrument routines, and neat survey patterns. The river looks simpler than it behaves, and that mismatch creates errors for anyone who trusts the view too quickly. Modern remote sensing helps, of course, but it also proves the same lesson rather than removing it. The 2019 Congo field campaign, led by researchers from Leeds and Kinshasa, covered 650 kilometres of the main stem and combined direct field measurements with satellite data. Their results showed that water surface conditions varied minimally along much of the surveyed reach, but significant changes occurred along a 150-kilometre reach at the outlet of the Cuvette Centrale wetland region. More importantly for our purposes, the authors concluded that existing satellite altimetry had insufficient spatial coverage there to detect major changes in water surface elevation. That is a remarkably useful warning. It means that even with modern tools looking from space, a large river can still hide important variations in plain sight. The problem is not that satellites are useless. The problem is that a smooth-looking surface can carry information that is too sparse, too incomplete, or too indirect to reveal the deeper behaviour that actually matters. You can have the overhead view and still miss the main point. The Middle Congo teaches a gentler version of the same lesson. In that long interior reach, the river is highly subcritical, with mild bed slopes and no great sequence of falls or rapids, and in many places it does present as broad, slow and stable. Yet even there, the 2019 study notes that in situ data are severely lacking because of the decline in gauging infrastructure, the lack of access, and the difficulty of working in a basin covered by dense forest. The same paper points out that dense forestry makes inundation extents difficult to observe and topographic data uncertain, which is one reason open water elevation measurements from satellite altimetry are so valuable. So even in the calmer looking sections, the view from above is not the same thing as understanding. The river can be wide, smooth, and apparently well behaved while still remaining poorly constrained in scientific terms. That is worth sitting with for a second. A system can appear quiet and still be underdescribed, not because scientists are careless, but because the environment itself makes simple observation surprisingly weak. This is exactly where the Congo starts to feel unlike the ordinary mental picture most people carry of a river. In a familiar river, surface appearance gives at least a rough clue. A rough surface suggests rough conditions. A broad calm reach suggests safer water and easier movement. That logic does not disappear in the Congo, but it becomes much less dependable. In the lower reaches, the annual discharge is enormous. The gradient steepens sharply. The bedrock channel introduces deep pools and constrictions, and the resulting flow structures create vertical and lateral separations that can matter more than the shoreline map. Smithsonian's reporting on the lower Congo expeditions captured the biological implication clearly. The river's power, depth, speed, and turbulence seem to divide populations from within fresh water itself, creating barriers where outsiders would expect connectivity. So a surface that reads as one body of water may function as several distinct habitats, divided not by dry land but by the force of water. That is a different kind of hidden geography. One of the strangest examples of this hidden geography involves fish that should not make sense if you only trust the surface view. The lower Congo's famous blind cichlid, Lamprologus lethops, has reduced pigmentation and severely reduced eyes, traits associated with life in darkness. In the USGS and AMNH work, researchers propose that such fish live in very deep portions of the river and are sometimes brought upward by strong upwelling currents. The problem is that they appear adapted to the pressure of those depths. When forced upward too quickly, they can suffer catastrophic decompression and die. This idea is discussed both in the USGS conference paper and in later research outreach pieces on lower Congo fish diversity. Think about what that means. A stretch of river that may not look especially alien from the bank can contain pressure environments so different from the surface that an animal dragged upward through them can be fatally damaged by the trip. That is not ordinary river business. That is a hidden vertical world under fresh water, concealed beneath a moving surface that often gives no honest preview of what lies below. And once you know that, the view from above begins to feel almost rude in its simplicity. The river keeps offering an outline when what matters is the interior. It gives width when the real story is depth. It gives a path when the truth is separation. It gives a surface when the crucial action is happening in layers, in shear zones, in recirculation cells, in sudden constrictions, in pressure changes, in dark channels, and in currents that can do the ecological work of mountain ranges. This is why the Congo can frustrate first impressions so effectively. It is not that the surface lies outright, it is that the surface is incomplete, in a place where incompleteness can become a major error. For scientists, that creates a constant temptation to underestimate. For everyone else, it creates the strange feeling that the river remains ordinary until the details begin arriving one after another, and the ordinary part quietly disappears. So when people say the Congo looks calm from above, they do not mean it always resembles a polished sheet of glass. They mean that distance smooths the truth. The map calms it, the satellite calms it, the broad aerial view calms it. Even the human habit of putting rivers into the category of familiar landscape features calms it. But the measurements tell another story, the biology tells another story. The survey crews in pirogues tell another story. The missing bathymetry tells another story. And once you stop expecting the surface to explain the system, the next question becomes unavoidable. If the river can conceal so much motion, separation, and force while still looking readable from above, Then how deep does that hidden structure really go? And what exactly is happening down there where light, pressure and current stop behaving like ordinary river conditions and start behaving like something much more severe? Once you stop trusting the surface to explain the river, the next thing you have to deal with is depth. Not ordinary river depth, where the water gets darker, colder, and perhaps mildly unfriendly before returning to more familiar behaviour. The lower Congo takes that idea and pushes it far past the point where most people still think in river terms. Direct field measurements by USGS researchers found maximum depths in excess of 200 metres, and their 2008 survey data indicated one reached deeper than 220 metres, which is why the lower Congo is widely described as the deepest river on Earth. The same work also found water velocities greater than 4 metres per second. So before we even start talking about what lives down there, or what the current does down there, it helps to be clear that this is not simply a deep river. It is a river with sections that behave like submerged terrain. That distinction matters because most of us imagine rivers as broad, mostly open channels, with a bottom that may be muddy or rocky, but is still conceptually simple. The lower Congo does not cooperate with that image. USGS descriptions of the river's lower course note a drop of roughly 270 metres from Malibbo Pool through the gorges of the Crystal Mountains to the Atlantic over about 498 kilometres, with 66 falls and rapids along the way. In the Bulu Reach, researchers found bedrock-controlled geometry, narrow constrictions, deep pools, dramatic changes in bed topography, and flow patterns shaped as much by the shape of the channel floor as by anything visible on the surface. That is why the word abyss is not especially exaggerated here. It is not a literary flourish placed on top of ordinary fresh water. It is a way of admitting that some sections of the lower Congo have the vertical scale and internal complexity of a hidden canyon system, and rivers are not supposed to do this to our intuition. Lakes, perhaps. Fjords, maybe. Offshore trenches, certainly. But a river that can exceed 220 metres in depth while still forcing huge discharge through constricted reaches creates a strange mental mismatch. It is still fresh water. It is still moving inland water toward the sea. Yet it can contain low-light habitats, steep internal relief, and pressure changes severe enough to leave biological evidence behind. The 2020 Genomic study on the blind cichlid Lamprologus lethops says the species is endemic to the lower Congo, and that available evidence suggests it inhabits deep, low-light habitats. The authors also note that lower Congo canyons with depths greater than 220 metres have been recorded, and that all known samples of this fish have been recovered dead or moribund at the surface in a short stretch near Bulu and Luozi. That is not how people usually talk about riverfish, and it is a strong hint that the world below the surface is operating under conditions that the bank does not prepare you for. There is something deeply unsettling about a freshwater fish that seems to belong to darkness. Lamprologus lethops is the only known blind cichlid. Its lack of pigmentation and reduction of image-forming eyes have made it important to evolutionary biologists, but its condition also tells a blunt environmental story. Fish do not lose useful structures for no reason. In this case, the OUP study points to a species from a riverine setting that has accumulated changes associated with life in light-poor habitats. Earlier field observations summarised by the same paper note that some recovered individuals had subcutaneous gas bubbles and fenestrated gas bladders, signs consistent with catastrophic decompression following rapid ascent from depth. In plainer language, something appears to be dragging or forcing these fish upward from a deep environment so quickly that the trip itself injures them. That is a very serious clue about what the lower Congo is hiding beneath its surface. The earlier USGS and MNH field reports give the hydrological side of that clue. In the Bulu Reach, the river's flow was described as highly energetic, with turbulent and secondary flow structures spanning the full depth of the water column, in places up to 165 metres deep. Researchers also found high shear, high-velocity zones that isolate flow separation regions near the banks from one another and from the opposite bank. This is a crucial point. The river is not just deep, it is dynamically deep. The full column of water is involved. Motion is not restricted to a brisk upper layer floating over some quieter bottom. The depth itself is part of the engine. Water is plunging, rotating, separating and rising again in ways that matter from top to bottom. That makes the word abyss feel less like drama and more like field shorthand for, below this point, the river is doing far more than you can see. In one especially striking section of the USGS analysis, researchers describe coherent structures spanning the full 160-metre depth of a deep pool, with large persistent cells of upwelling and downwelling coexisting with turbulence and vertical jets that rapidly transport water between the benthic zone and the surface. Maximum secondary velocities exceeded 3 metres per second, maximum vertical velocities exceeded 1 metre per second, and depth-averaged vertical velocities exceeded 75 centimetres per second in one bend where plunging flow met upwelling water. Those are not small adjustments within a gentle river reach. They are vertical exchanges strong enough to move water, suspended material, and potentially organisms between very different pressure and light conditions. When you hear that, and then remember the blind fish arriving at the surface injured, the abyss stops being an image and becomes a mechanism. This is why the lower Congo has been so important to biologists. In most river systems, the main questions about isolation are horizontal. Can fish cross from one tributary to another? Can a waterfall block movement? Can a dry season cut populations apart? In the lower Congo, some of the most important barriers are hydraulic and vertical. The river itself creates separation by force, not merely by distance. AMNH's more recent summary of Lower Congo research describes the region as the deepest river in the world, exceptional in its speed and turbulence, and home to more than 300 known fish species. It also notes that the intense hydraulics of the rapids and deep canyons wall off fish populations into what amount to islands in the water. That phrase is useful because it captures what depth does here. The abyss is not just empty space under the boat. It is part of the architecture that divides life into pockets, zones, and neighbourhoods that can remain effectively apart even inside one river. And the division is not polite. It is not as though the river has placed a tasteful rope barrier between one habitat and the next. The USGS hydraulic surveys found that even when the channel widens, downstream flow is often concentrated into a jet whose size and location are largely determined by the thalweg and channel orientation. In some places, local bedrock controls have a major effect on flow even where there are no obvious waterfalls or rapids. Dramatic bed changes show up in repeated transects. That means the river floor is not some passive backdrop. It is shaping and redirecting force in ways that carve out deep lanes of fast water beside calmer-looking pockets and deep pools beside rougher shallows. To an outsider, that still sounds manageable until you realise that the boundaries between those zones may be invisible at the surface and physically punishing underneath. The practical challenge for researchers is obvious once you picture it properly. Imagine trying to understand a place where the floor drops hard. The current accelerates through narrow paths. The river can widen without actually becoming easier, and the water column itself is vertically active. Add to that the reality that the lower Congo remained poorly measured for decades. The USGS paper on direct hydraulic measurements says plainly that there is little basic hydrologic and hydraulic data available for the lower Congo, despite its geologic, geomorphic, biologic and economic significance. That is the sort of sentence scientists write when they are trying to sound calm about a problem that is actually quite irritating. It means they were attempting to understand one of the most extreme freshwater systems on Earth, while still lacking the kind of baseline measurements that would be considered ordinary elsewhere. An abyss is hard enough to study when you know where it is. It is even harder when you're still figuring out how many abysses the river has made for itself. There is also the matter of navigation. which becomes much more revealing in this section of the story than it first appears. The same USGS survey notes that large vortices, some 3 to 4 meters in diameter, could open up under the pirogue and make it difficult to hold a planned course. High velocities in those vortices made navigation from shore to shore a challenge. That is not a dramatic retelling from a sensational documentary voiceover. That is what the measurement team itself reported. It tells you something valuable about the underwater abyss, because the danger was not only that the water was moving fast, it was that the shape and energy of the river below were producing sudden rotating features strong enough to disrupt controlled survey work from the surface. Even when researchers knew they were in difficult water, the water still had additional opinions. One of the most useful ways to think about the lower Congo is to stop imagining a single bottom and start imagining stacked terrain. There is the visible river channel, yes, but under that lies a shifting arrangement of slopes, holes, ledges, constrictions, plunge zones, and deep trenches shaped by bedrock and enormous discharge. The USGS work repeatedly points to dramatic topographic changes and to flow behaviour controlled by local channel form. The OUP paper on Lamprologus lethops adds that the lower Congo's hydrology is extraordinarily complex, with some of the world's largest rapids, high-velocity in-stream flows, and shallow rapids adjacent to canyons deeper than 220 metres. That pairing matters. Shallow, violent water beside deep, low-light water is not an ordinary river arrangement. It means the lower Congo can place extremes directly next to each other, which helps explain why species can become isolated so effectively, and why the river can feel so difficult to predict. This is also where the abyss begins to change the emotional tone of the science itself. Up to a point, river hydrology feels like a technical discipline. You measure discharge, slope, velocity, depth, sediment load, channel geometry. It is precise and useful. But once the channel becomes this deep and this active, the data begin pointing towards something more uncomfortable, which is how much of the environment is inaccessible to direct human intuition. We are land animals with a strong preference for seeing the thing we're talking about. The lower Congo often refuses that preference. The most important pieces of the system are happening below opacity, inside high-energy flow, in places that cannot be casually observed and are difficult even to instrument. So when scientists describe it as mysterious from a hydraulics perspective, they are not trying to be romantic. They are being specific about the fact that the abyss beneath the surface is not just deep. It is hard to witness. The fish keep forcing that point back into view. More than 300 species have been identified in the lower Congo, and around 30% were described in the USGS summary as found nowhere else on Earth. AMNHE's 2024 overview again emphasises both the species richness and the river's exceptional speed and turbulence. This concentration of biodiversity in such a hostile hydraulic setting seems strange until you accept that the abyss is acting like a sorting system. Deep canyons, violent currents, and hidden flow barriers do not merely make life difficult. They divide it. They trap lineages on one side of a current, in one recirculation zone, near one bank, above one canyon lip, or below one severe hydraulic boundary. Given enough time, separation becomes divergence. The abyss is therefore not just a place beneath the water. It is one of the reasons the lower Congo became a machine for making uniqueness. And even that does not capture the full oddness of it, because the abyss is active in both directions. We tend to imagine depth as simply downward, as if the danger lies in sinking, but the lower Congo keeps showing that upward movement can be equally important. Upwelling is part of the story. Vertical jets are part of the story. Fish apparently forced to the surface too quickly are part of the story. Sediment being stirred and transported by secondary flow is part of the story. In the Bulu Reach, the USGS team observed suspended sediment correlated with secondary flow vectors, as well as strong vertical exchange between the bottom zone and the surface. So the abyss is not sealed away from the upper river, it communicates violently. What is below does not stay below in a quiet, orderly way. It surges upward when the channel geometry and flow demand it. That makes the whole river feel unstable in a very specific sense. Layers do exist, but they are not always content to stay layered. This is one reason the lower Congo can make even familiar scientific language sound slightly ominous. Terms like bathymetry, discharge, recirculation, shear, and secondary flow are perfectly normal in hydrology. Yet here they begin to read like clues in a crime report. Bedrock control, deep canyons, high shear zones, persistent upwelling, catastrophic decompression, fish found dead or nearly dead at the surface, large vortices opening beneath survey craft. Any one of those details on its own is interesting. Put together, they describe an underwater abyss that is not passive, not smooth, and not content to let the rest of the river behave like a regular large waterway. It is as though the lower Congo keeps insisting that beneath every calm phrase there is something more physical and less reassuring waiting to be measured. None of this means the river is unknowable. That would be too easy, and scientists dislike giving rivers the satisfaction. It means the lower Congo has required a more serious level of respect than outsiders often expect. Researchers have measured it. They have mapped pieces of it. They have tied biological isolation to hydraulic structure. They have shown that the blind fish is not an odd fairy tale detail, but part of a consistent story about deep, low-light habitats and extreme vertical motion. What remains frightening is not ignorance in the simple sense. It is the combination of knowledge and force. We now know enough to say that this abyss is real, deep, energetic, biologically consequential, and difficult to work in. That is often more unsettling than not knowing at all. A mystery can be comforting if it stays vague. A measured abyss is something else. So when the Congo begins to feel less like a river and more like a vertical system hidden under a river, that feeling is earned. Beneath the surface there are deep canyons, strong jets, recirculation cells, violent shear zones, and dark habitats that have shaped the bodies of animals living inside them. There are stretches where the whole water column participates in the flow. There are places where rising water can be as dangerous as sinking water. There are sections where the bottom controls the current so strongly that the river's true structure becomes legible only through instruments and dead fish arriving with bad news. By the time you put those pieces together, the word abyss stops sounding dramatic and starts sounding almost annoyingly practical. It is the shortest, honest word for a river that contains hidden depth with consequences. And once that hidden depth is in view, the next thing that becomes impossible to ignore is motion. Because a deep river is one thing. A deep river whose currents can isolate species, punch jets through widening channels, and rearrange what counts as reachable water is something far more serious, which is where the flow itself starts taking over the story. If the previous section was about depth, this one is about what that depth allows the water to do, because the lower Congo is not frightening only because it is deep. A deep hole in still water is one kind of problem. A deep, narrow, bedrock-shaped channel moving an enormous volume of water is another. The Congo's average discharge at its mouth is about 41,000 cubic meters per second, and near Pool Malibbo the lower river begins a steep descent through rapids, cataracts, and deep pools on its way to the Atlantic. By the time that water is forced through the lower course, the question is no longer whether the current is strong. The question is what, exactly, that strength is doing to everything inside it. A lot of rivers carry things. The lower Congo does more than carry. It sorts, separates, redirects, traps, and sometimes ejects. USGS researchers working in the Bulu Reach found a river that was not flowing as a single, neat body from one bank to the other. Instead, the flow was highly energetic, structured by bedrock, and organised into turbulent and secondary motions that could span the full depth of the channel, up to 165 metres in that reach. Regions of flow separation near the banks were cut off from one another by high shear, high velocity zones, with depth average speeds that could exceed 4 meters per second. That is a very important detail, because it means the current is not merely pushing downstream, it is building internal boundaries. Water itself becomes the thing that divides the river into places that are close on a map and hard to reach in reality. That is why the current in the lower Congo can be thought of as a force that rearranges a world. Not the whole planet in one dramatic sweep, obviously. Rivers are powerful, not magical. But inside the river, for the animals living there, for the shape of the channel, and even for the way material leaves the continent and enters the sea, these currents keep deciding what can mix and what cannot. A human eye sees one river. A fish may experience a bank eddy, a narrow rocky shelf, a protected pocket behind submerged structure, and then, just a short distance away, a corridor of water so fast and so unstable that it functions like a wall. The result is that habitat is defined not only by location, but by force. The river is making geography out of motion. Biologists have been trying to explain that for years because the lower Congo has long looked strangely overstocked with uniqueness. The American Museum of Natural History has described the lower Congo as home to more than 320 fish species in only about 350 kilometres of river, with roughly 90 of those species found nowhere else. A separate AMNH summary notes that some of the rapids in the system are among the fastest and most turbulent in the world, and that diversification there can happen over distances as small as 1.5 kilometres. If that sounds absurdly compressed, that is because it is. In many places on Earth you would need much larger barriers to get such strong separation. In the lower Congo, currents do that work on very small spatial scales. They turn a short stretch of river into a collection of partly isolated living zones. There is a tendency, when hearing something like that, to imagine rapids as the only culprit. Whitewater, after all, looks dramatic and receives most of the attention. But the lower Congo is more difficult than that. The visible rapids matter, certainly. They can block movement, narrow options, and favour animals that can hold position or use protected margins. Yet the strongest lesson from the hydrological work is that the unseen current structure matters just as much. In the Bulu Reach, coherent bank-to-bank flow structures were absent. The river did not behave like one continuous cross-section. That absence is what makes the system so effective at dividing life. A fish on one side is not simply being asked to swim across ordinary moving water. It may have to cross a very fast, high-shear, unstable zone whose force exceeds what its body can manage. At that point, the current is not scenery. It is a border. This is not just a plausible story told after the fact. Genetic work backs it up. A 2010 study of two cichlid genera from a 100-kilometre stretch of the lower Congo found patterns of phylopatry and genetic isolation among the highest reported for any African cichlids over a comparable scale, and the authors argued that these patterns are generated and maintained by the extreme hydrology of the river. That is a compact way of saying the current is helping to split populations apart and keep them apart, not because the fish are lazy, not because they forgot where the opposite bank is, but because the water between them is acting as a serious dispersal barrier. There are very few places where such a short piece of fresh water behaves with that kind of evolutionary authority. The current also changes the meaning of distance. In ordinary conversation, 1.5 kilometres sounds small. It is the sort of distance people walk without much thought, when looking for coffee or pretending they enjoy a quick stroll. In the lower Congo, AMNH researchers found that diversification can happen over distances that small, because the rapids and current structures are so effective at keeping fish populations apart. A short distance in easy water is one thing. A short distance through a hydraulic barrier is another. This is one of the river's most unsettling habits. It keeps taking ordinary units of measurement and making them behave differently. Width does not mean ease of crossing. Proximity does not mean contact. One river does not mean one shared habitat. There is a good practical reason why the current becomes so dominant here. The lower Congo is not just a large river with some rapids added to make it interesting. It is the downstream expression of an immense basin feeding into a steep, geologically controlled lower reach. USGS describes a 270-metre descent from Malibbo Pool through the Crystal Mountains to the Atlantic over about 498 kilometres. AMNH's field summary puts the flow spilling downslope from Pool Malibbo at roughly 50,000 cubic metres per second as it enters the gorge and churns through what they call the world's most extreme rapids. Once that much water begins negotiating steep gradient, constricted channels, cliffs beneath the surface, and abrupt bed changes, the current stops being a single number and becomes a behaviour. It folds, it accelerates, it peels off banks, it rises from depth, it spins off vortices. It does not simply move downstream in a straight sensible manner because the channel is not offering it a straight sensible path. That is where the river begins to feel almost mechanical, though not in a clean or predictable way. Think less of a pipe and more of a giant rocky system of chutes, drops, shelves, troughs and bends, except all of it is hidden under dark water moving at serious speed. In the lower Congo, large whirlpools have been observed and parcels of water rise from the depth strongly enough to capsize small boats. AMNH's field account describes these whirlpools and upwelling parcels directly, while the USGS hydrology work describes strong secondary flow, recirculation, and full-depth turbulent structure. Put together, those findings say something simple and unpleasant. The current is not just horizontal, it is vertical as well. Water is being driven downward, drawn sideways, and then forced upward again in places where the channel shape makes that possible. So the river is not merely moving across the landscape. In key reaches, it is constantly rearranging its own internal layers. That vertical motion matters because it changes what home means for an organism living there. In a calmer river, a fish can often move through the water column or across a channel with some degree of choice. In the lower Congo, those decisions are constrained by a moving hydraulic architecture. Protected areas may exist only in certain pockets. Crossing from one to another may require passing through water that is not just faster, but physically destabilizing. This helps explain why so many fish in the lower Congo are localized and, in some cases, visibly unusual. It is not that the river makes odd creatures for entertainment, it is that different pieces of the river reward different solutions. In one place, a fish that can cling near rocky margins may do well. In another, a fish adapted to darkness and depth may persist in a low-like canyon habitat. In yet another, body shape and swimming style may be tuned to survive swift boundary flows. The current is not merely filtering species, it is assigning terms. This is why AMNH researchers ended up talking about brick walls made of water. The idea is not theatrical once you see the evidence. In one part of the lower Congo, two populations can occupy opposite sides of the river and still remain effectively separated because the current between them is stronger than their ability to cross and return. AMNH's field account explains that if the water is more powerful than a fish's ability to swim, then it behaves like a barrier in the same practical sense as a wall. That comparison works because a barrier is defined by consequence, not material. Stone, ice, dry land, or violent water all achieve the same result if they prevent movement and gene flow. In the lower Congo, current has taken on that job with unusual efficiency. The current also decides what happens to material that is not alive. Suspended sediment, organic matter, and whatever else the river picks up are not drifting through a peaceful corridor. In the lower Congo, motion near the surface is tied to motion near the bottom by full-depth turbulence and strong vertical exchange. The USGS team specifically connected suspended sediment patterns in the Bulu Reach with secondary flow vectors, which means the flow structure helps determine where material is carried, where it is lifted, and where it is likely to settle or remain in motion. For life in the river, that affects habitat, visibility, feeding, and the condition of the bottom. For scientists, it means the current is not simply a transport belt. It is an active sorting process whose details depend on hidden channel form. A useful way to picture this is to stop imagining a broad, even riverbed, and start imagining a rough underwater landscape over which a huge amount of water is being forced. Once you do that, current stops sounding like something separate from topography. The two become partners. Bedrock controls the channel shapes the flow. The flow then reinforces some local patterns, carves others, and keeps producing the conditions that isolate populations and challenge measurements. USGS called the Bulu Reach bedrock controlled for a reason. The current there is not free to choose any path. It is being organised by the shape of the river itself, which then makes the organised motion more extreme. This is one of the reasons the lower Congo remains so hard to summarise cleanly. The river's power is not just a matter of volume. It is a matter of volume meeting shape in exactly the wrong mood. The phrase, rearrange a world, begins to feel even less exaggerated when you follow the Congo beyond the river mouth. A 2022 Nature Communication study documented seafloor turbidity currents originating from the Congo River mouth that travelled more than 1,130 kilometres while accelerating from 5.2 to 8.0 metres per second. In a single year, those flows eroded an estimated 1,338 to 2,675 million tonnes of sediment from one submarine canyon, equivalent to 19 to 37% of the present-day annual suspended sediment flux from all rivers combined. That is an astonishing result. It shows that the Congo's energetic transport does not politely stop at the shoreline. Flood-related processes linked to the river can prime and trigger canyon-flushing sediment flows far offshore, connecting river discharge to major reshaping events on the deep sea floor. So the current is not only rearranging life within the river, it is helping rearrange sediment pathways between Central Africa and the Atlantic abyssal plain. There is something almost rude about that level of continuity. We like categories. River here, ocean there, freshwater processes in one column, marine processes in another. The Congo keeps making those columns leak into each other. Nature's study showed that river floods and often spring tides were associated with these canyon-flushing turbidity currents, sometimes after delays of weeks to months. That means the river mouth can act less like a neat endpoint and more like a storage and release system, collecting flood sediment and then sending it seaward in bursts, powerful enough to erode huge volumes of seabed. If you wanted a concrete example of a current rearranging a world that would qualify, the world in question just happens to include a submarine canyon system. Back in the river itself, the same logic holds at smaller scales. The lower Congo's current can rearrange a fish community without moving a single rock in front of your eyes. It can do that by changing what counts as reachable. If a stretch of white water, a velocity jet, or a deep shear zone blocks movement for long enough, populations that once shared genes begin drifting apart genetically. Give that process enough generations and the current will have helped create biological difference out of separation. The study of two lower Congo cichlid genera makes that point rather bluntly. The observed genetic structure over that 100-kilometre stretch was unusually strong, and the authors traced it back to extreme hydrology. Water flow, then, is not only shaping ecology in the present tense, it is helping write evolutionary history. This is exactly why the lower Congo bothered earlier assumptions about fish evolution. For a long time, it was tempting to treat rivers as places where fish could more or less go anywhere within a connected channel. Land animals face mountains, glaciers, deserts, and coastlines. Fish, in that simplified view, live inside the thing that connects them. The lower Congo exposed the weakness in that idea. It showed that fresh water can contain internal barriers just as effective as some barriers on land. Those barriers do not need to be made of rock rising above the water. They can be made of the river's own speed, turbulence, depth, and bed geometry. In that sense, the current is not simply rearranging fish. It is rearranging the way scientists think about what a river is capable of doing. There is also a human dimension to this, and it is worth keeping in view because otherwise the story can become too tidy and academic. These currents are not only shaping fish genetics and deep-sea sediment transfer, they're also making fieldwork dangerous and routine movement more complicated. A MNAS account describes whirlpools large enough to capsize small boats. Earlier surveys required kayakers and pirogues to gather measurements, and those teams encountered water behaviour unlike anything they were used to. That matters because it reminds us that the current is not a diagram in a journal article, it is a lived force. Researchers, local boat operators, fishers, and river communities all meet the same water, though not always for the same reasons and not with the same tools. The river's power is democratic in the least comforting sense. It does not check credentials before becoming difficult, so by this point, the lower Congo starts to look less like a single river and more like a moving system of decisions. The current decides which margins stay connected and which become isolated. It decides whether a fish can cross, whether a survey line can be repeated cleanly, whether suspended material rises or settles, whether a deep canyon habitat stays hidden, and whether flood sediment waits quietly at the river mouth or eventually rushes into the deep sea. Current can sound like a mild word, almost a polite one, the sort of thing you discuss while standing safely on a bridge. In the lower Congo, it means force organised by depth, slope, and rock, acting over time until life and landscape begin to bear its imprint. And once a river reaches that level of force, another difficulty appears. The current may be measurable in pieces, but not easily visible as a whole. Its strongest structures are often happening in dark water, below glare, below foam, below whatever the eye can briefly interpret from the surface. That is where the next part of the story starts to press in, because a river this active is one thing. A river this active in conditions where light drops away and instruments begin working at the edge of practicality is another. A river can be dangerous, and that is one kind of problem. A river can also be difficult to measure, and that is a different problem entirely. The lower Congo manages to be both at the same time. It is deep enough, fast enough, and physically awkward enough that even when scientists arrive with modern tools, they do not simply lower a device into the water and receive a neat little answer in return. They have to negotiate with depth, current, missing data, equipment limits, and the basic inconvenience of trying to map a place that does not want to hold still. This is where the story becomes less about dramatic water and more about the practical frustration of a measurement. Because once the current is hidden in dark water, once the river floor drops away, once the flow begins folding vertically as well as horizontally, the instruments start doing what instruments always do in hard environments. They work, up to a point, then the river starts charging extra. In the 2008 Lower Congo survey, the USGS and its collaborators did not arrive with toy gear and hopeful expressions. They used acoustic Doppler current profilers, differential GPS, and echo sounders to collect velocity and bathymetry data, and they brought 3 different ADCPs into the field: 300, 600, and 1200 kHz units. But because of the river's great depth, the 300 kHz instrument was used almost exclusively for the main data discussed in the Bulu study. That alone tells you something. Lower frequency acoustic instruments can penetrate deeper water better than higher frequency ones, though they come with their own trade-offs. The team also relied on collapsible solar panels and vehicles to recharge equipment, which is the kind of detail that sounds dull until you remember that it means the research environment was remote enough that basic electrical certainty was not a given. Scientific fieldwork often looks elegant in the final paper. In the actual river, it can look like trying to keep expensive electronics alive while the water behaves like it has personal objections to your project. The instruments themselves have limits before the Congo even enters the picture. USGS guidance on ADCP measurements explains that these profilers cannot measure the whole water column directly. They miss the very top because of instrument draft and blanking distance, and they miss the lower part near the bed because of side lobe interference. In practical terms, there is always an unmeasured zone near the surface and another near the bottom, and the discharge in those zones has to be estimated from the portion that was successfully measured. Lower frequency ADCPs can probe deeper water than higher frequency ones, but they also require larger depth cells and longer blanking distances. So even in a controlled setting, the device gives you a profile with edges you must reconstruct indirectly. That is manageable in many rivers. In the lower Congo, where the bed can drop sharply, the current can shift violently with depth, and the deepest parts are among the most scientifically important. Those blind zones become much more consequential. The river is difficult exactly where the instrument is least omniscient. There is another awkward detail. A DCPs work by sending sound into the water and reading the backscattered return from suspended particles. The USGS manual notes that pure water is acoustically transparent, so there must be enough particulate matter in the water column for the instrument to get a usable signal. But too much sediment can create the opposite problem. High sediment concentrations can attenuate the signal before it travels through the water column and back, and sediment near the bed can confuse bottom tracking and bias boat velocity measurements. The manual also warns about moving bed effects, in which transported sediment near the bed makes the instrument think the boat is moving differently than it really is. In plain language, the machine needs the water to cooperate acoustically, and the water is under no obligation to do so. A river with strong flow, depth, suspended material, and complex bed conditions is the sort of place where measurement turns into interpretation very quickly. The instrument is not a magic eye. It is another participant trying not to get fooled. Now place those limits inside the lower Congo. The first direct measurements made in 2008 showed maximum depths in excess of 200 meters and maximum water velocities greater than 4 meters per second, with local bedrock controls having major effects on the flow and dramatic changes in bed topography evident across transects. The river between Kinshasa and the Atlantic drops steeply, and in the first 130 kilometers below Malibbo Pool, there is a series of extreme rapids that had not been successfully descended and documented until 2008. That means the team was trying to profile a river that was not merely deep, but geologically aggressive. It had a steep bed slope, expansions and contractions, bedrock control, hidden relief, and energy levels high enough that earlier satellite-derived estimates had already hinted at depths greater than 100 meters and velocities in excess of 7 meters per second in some areas. Even before the finer results came in, the river was already telling scientists that standard expectations about freshwater fieldwork were due for revision. And then there was the matter of actually moving through it. The remoteness of the survey sites and the lack of navigable water in the lower Congo required the use of local boats and operators. In the Bulu work, the primary survey craft was a traditional pirogue made from a single hollowed-out log and fitted with a 15-horsepower outboard motor. The ADCP was mounted in a tethered trimaran and towed alongside the manned boat. That is already a sentence that makes the whole operation sound less like a laboratory procedure and more like a delicate agreement with chaos. The study notes that the swift and often turbulent flow, combined with limited communication with the operators, made it difficult to remain on course for repeated transects. In the broader measurement paper, the team adds that large vortices, some 3 to 4 meters in diameter, would open beneath the pirogue and make it difficult to hold a planned line. High velocities coupled with those vortices made navigation from shore to shore a challenge. So the struggle was not theoretical. The instrument had to be moved through the river with enough stability to make the data meaningful, and the river kept objecting. That is the kind of thing people often forget about hydrology. Before there is a graph, there is a boat trying to follow a line. Before there is a paper explaining velocity gradients, there is somebody in real water trying not to let the survey drift into nonsense. The lower Congo is an unusually clear reminder that precision begins with physical control, and physical control is hard to maintain in a river that throws whirlpools, vortices, and high shear currents at the platform carrying the sensors. The 2009 measurement paper says plainly that the nature of field and river conditions, together with time and logistical constraints, made it difficult to adhere completely to standard ADCP discharge protocols. That line is wonderfully understated. It translates roughly to, the river was difficult enough that some of the usual best practices had to give way to survival, practicality, and whatever usable data could be safely collected. Science likes repeatability. The Lower Congo prefers negotiation. Even when the team got the equipment working, the river still found ways to complicate things. The same USGS report ends with a set of suggestions for future work that reads, "To anyone familiar with field science, like a list written after a long week. Use a dual frequency, survey-grade echo sounder. Use a boat operator experienced in velocity data collection in this environment and a boat suited to conditions in the Lower Congo. Identify and remedy the source of the compass problems experienced in this work. Include more transects with navigation software and pre-planned lines, and obtain stationary measurements where possible. Use RTKD GPS to provide accurate boat velocities for ADCP measurements and help quantify local water surface slopes." That is an unusually candid way of saying the river exposed several weaknesses at once. Platform stability, directional reliability, acoustic coverage, navigation control, and local slope measurement. The instrument did not fail in some melodramatic way. It simply entered a place where every part of the measurement chain became harder than normal. There is also a more practical kind of darkness here, and it has nothing to do with sunlight. It is the darkness created by missing records. The Lower Congo is difficult to study in the field, but the larger basin also suffers from a long decline in ground-based monitoring. The 2009 USGS measurement paper notes that hydrological data on the Congo are often limited to documents dating back to colonial times and the brief period after, and that many gauging stations in rural areas were abandoned after independence. A 2023 paper in Communications, Earth and Environment says the basin was relatively well gauged prior to 1960, but today only a few active hydrological gauges exist across it. That matters because every difficult field campaign is trying to compensate for a long period of sparse observation. When scientists head into the Congo with modern instruments, they are not dropping those tools into a dense, reassuring archive of continuous measurements. They are often trying to fill major gaps in one of the least well-constrained large river basins in the world. In that sense, the darkness is informational as well as physical. There are simply fewer lights on. Naturally, satellites are supposed to help with that, and they do help, but even they run into the basin's habit of being difficult in the right places. A 2019 field campaign covering 650 kilometres of the Congo's main stem combined in situ measurements of river depth, flow rate, velocity, and water surface elevation with satellite data. The study found that along a key 150-kilometre reach, near the outlet of the Cuvette Centrale, significant changes in water surface behaviour were occurring that existing satellite altimetry did not have enough spatial coverage to detect. The authors say plainly that understanding remains poor for unmonitored systems where access is difficult, and they also note that satellites cannot directly measure bathymetry or discharge. That is a very useful correction to the common assumption that once you can look from space, the hard part is over. In the Congo, the overhead view is powerful but incomplete. It can tell you a great deal, but not the whole story, and sometimes not the most urgent part of the story. This is where the word darkness becomes almost embarrassingly literal again. One of the strongest clues to the river's hidden world comes from a fish that seems to have been shaped by it. The only known blind cichlid, Lamprologus lethops, is endemic to the Lower Congo, and genomic work published in 2020 says the available evidence suggests it inhabits deep, low-light habitats. Earlier work discussed in the same study noted that recovered individuals sometimes showed signs consistent with rapid decompression after ascent from depth. That matters here because it tells us the Lower Congo is not just hard for instruments to map. It is hard enough, dark enough and deep enough that one of the best witnesses to the hidden environment is a fish carrying that environment in its body. Reduced eyes, reduced pigmentation, low light adaptation, possible decompression injury after being forced upward. Those are not decorative curiosities, they are biological measurements made out of tissue. When the instruments struggle, the animals sometimes end up supplying the missing paragraph, and it is worth noticing how the scientific picture forms here. It is not a single machine solving the river in one elegant pass, it is a patchwork. Acoustic surveys reveal bed shape and velocity structure. Echo sounders supplement depth estimates. GPS helps untangle boat motion. Satellites provide broader context but leave important spatial gaps. Historical records, where they still exist, anchor longer-term discharge knowledge. Biological evidence points to habitats the instruments have trouble sampling directly. Even public outreach from the USGS after the 2008 expedition emphasised that scientists were measuring places deeper than 700 feet in a dugout canoe, crossing rapids and whirlpools. That image captures the real mood of the work rather well. It is modern measurement, yes, but not in a clean, remote, button-pressing sense. It is modern measurement dragged physically through a river that still forces people into close contact with its worst habits. So when we say the darkness is where instruments struggle, the point is not that the lower Congo defeats science. It is that the river forces science to proceed in layers, with caveats, and with a level of humility that many environments do not demand so consistently. The current obscures the line you want to hold. The depth forces you into lower frequency trade-offs. The instrument misses the top and bottom of the water column. Sediment and moving bed effects can distort acoustic readings. Gauges are sparse. Satellite coverage is incomplete in crucial reaches. The deep habitats are low light and hard to observe directly. This is why the lower Congo still feels unsettling to scientists. They do not lack tools. They lack the luxury of easy conditions. The river keeps making every method work harder than it would somewhere else, which is a polite way of saying the measurements arrive only after a fight. And that tension produces one of the strangest outcomes in the whole story. The place becomes known not only through direct measurement, but through the kinds of living things that direct measurement helps explain. The lower Congo's darkness is written partly in velocity maps and bathymetric transects, and partly in bodies that look as though they were assembled for a world the human eye rarely sees. Once you realise that, the next step is almost unavoidable, because the river is no longer just a difficult hydraulic system. It is a habitat that has been quietly training its inhabitants to survive in conditions that still make our instruments work for every honest answer. By the time the instrument starts struggling, another kind of evidence begins to matter more. The river's inhabitants have been taking notes for a very long time. Not with paper, obviously. Not with a neat field log tucked under a fin. They record the lower Congo in their bodies. The shape of a skull, the size of an eye, the use of pigment, the way a fish sits in current, the way it senses nearby objects, the way it holds itself close to rock instead of drifting upward. These are not decorative differences. They are answers to a place. And the place they answer to is so unusual that the lower Congo now contains more than 320 known fish species in only about 350 kilometres of river, with roughly 90 of them found nowhere else. MNH researchers have described some of these fishes as having long snouts, eel-like bodies, tiny eyes and colourless skin, which is about as close as a freshwater river gets to admitting that it has been running private experiments out of view. That is the first useful correction to make here. When people hear that the Congo hides a terrifying underwater realm, they often imagine one huge creature, one legendary beast, one convenient nightmare with teeth large enough to justify the story. The truth is more interesting and much less theatrical. The hidden realm is full of specialists. The lower Congo does not produce a single monster. It produces many narrow solutions. It makes fish that are built for darkness, fish that are built for current, fish that are built for tiny protected pockets beside violent water, and fish that are built for habitats so isolated that nearby populations can drift apart into separate forms over very short distances. This is why the river feels biologically strange. It is not because one species stands out. It is because so many species look as though they were shaped by different rooms inside the same building. The river is one address. The creatures inside it behave as if they evolved in separate apartments, each with its own plumbing problem. The clearest example remains Lamprologus lithops, the lower Congo's famous blind cichlid. It is the only known blind cichlid, and genomic work published in 2020 says the available evidence suggests that it inhabits deep, low-light habitats in lower Congo canyons. Researchers also reported that genes related to eye formation and pigmentation accumulated in activating mutations rapidly after speciation, and that the species carries genomic patterns consistent with a severe population bottleneck roughly 1 million years ago. That matters because it confirms what the fish already looks like it is trying to say. This is not a normal colourful cichlid that merely happens to live in an unusual river. It is an animal whose body has moved toward the logic of darkness. It lacks the normal visual toolkit and pigmentation of its relatives, and it seems to come from depths where those features are either less useful or not worth their cost. In a cave, people understand that story immediately. In a river, it feels almost offensive to common sense, which is probably why the fish has had such a hold on researchers ever since it was recognised for what it was. The details become even stranger once you look at how Lamprologus lithops is found. The same genomic study notes that all known samples have been recovered dead or moribund at the surface from a short stretch of the lower Congo near Bulu and Lwodzi. Some individuals were found with subcutaneous gas bubbles, and most had fenestrated gas bladders, signs consistent with catastrophic decompression following rapid ascent from depth. AMNH's field summary adds the vivid detail that this fish, known locally as Mondale Bureau or White Man's Office, has never been observed alive in normal conditions for long. One specimen died in Melanese Diasne's hand after showing the kind of trauma associated with surfacing far too quickly. That means the fish is not simply adapted to a dim environment. It appears to be adapted to a pressure regime very different from the surface water, where people keep encountering it only after something has gone badly wrong. This is an extraordinary way for a river to reveal one of its creatures. The animal reaches us as evidence of a failed ascent. What makes that fish especially important is that its odd appearance is not being treated by researchers as a colourful anecdote. The OUP study explicitly compares the kinds of genomic changes in L. lithops to troglomorphic traits seen in cavefish, including losses tied to vision and pigmentation. At the same time, the authors are careful not to pretend the explanation is simple. Their results suggest that accelerated genetic drift after a strong bottleneck probably played a major role, perhaps helped by directional selection for losing traits that are physiologically expensive in a low-light habitat. That caution is useful. It keeps the story honest. The lower Congo did not wave a wand and turn a cichlid into a river cave fish overnight. The transformation seems to have involved real evolutionary history, reduced population size, and the long pressure of living in an environment where eyes and pigment offered less benefit than they once did. Even the uncertainty is revealing. When a river is capable of producing cave-like outcomes in open fresh water, the correct scientific response is not overconfidence. It is a longer stare. Still, the hidden realm is not populated only by pale fish that look as though they escaped from a broken basement aquarium. Many lower Congo species are built not for darkness alone, but for current. That becomes obvious in the cichlid radiations that researchers have traced through the rapids. A 2011 phylogenetic study found that the lower Congo assemblages of Steatocranus and Nanochromis qualify as riverine cichlid species flocks, and that their diversification within the lower Congo took place within the last roughly 5 million years, closely linked to the origin of the modern lower Congo system. The same study describes the river as split into 3 major biogeographic areas: each with its own assemblages and local endemism. So the creatures built for this realm are not just surviving a violent river, they are the products of a river that keeps dividing habitat into pieces and then giving each piece time to grow its own local specialists. That is how a hidden realm fills up, not with one dramatic act, but with repeated separation and repeated adaptation. Within those cichlid lineages, the bodies themselves begin to show how specific the river's demands can be. The same 2011 study notes obvious differences among Lower Congo Stitocranus, with some species being lower-bodied and others higher-bodied, and it suggests these forms correspond to different ways of living in strong current, either out on top of exposed stones or more tucked among them. Another study on swimbladder morphology found that Stitocranus tenanti has a considerably small swimbladder. That sounds like a minor anatomical footnote until you remember what a swimbladder does. In ordinary fish, it helps with buoyancy. In violent rapids, too much buoyancy can be a nuisance. A fish that wants to stay near the bottom, keep control, and avoid being lifted into faster water does not necessarily benefit from floating well. So this is one of those Lower Congo adaptations that makes immediate practical sense. The river has not made the fish elegant in the abstract, it has made it harder to push around. A similar story appears in Teleogramma, a clade of rheophilic rock-dwelling cichlids restricted to fast-flowing waters in the western Congo basin. One study describing a new species, Teleogramma obamaorum, notes that the Lower Congo and nearby habitats harbour endemic cichlid lineages with highly specialised morphologies, while AMNEH's field, reporting on Teleogramma brichardi, showed that populations caught on opposite sides of the river looked nearly identical in morphology, yet differed by around 5% in the DNA section examined. That contrast is useful. The fish can remain outwardly conservative, while the river quietly separates them genetically. The hidden realm, then, does not always announce itself with bizarre forms. Sometimes it works in subtler ways. Two fish may still look much alike to us, while the river is already treating them as residents of different hydraulic neighbourhoods. Appearance lags. Separation does not. Then there are the electric fishes, which bring a different kind of adaptation into view. In Central African waters, mormyrids navigate and explore dark and turbid environments using a specialised electric sense. A well-studied example is Gnathonymus petersi, the elephant-nose fish, which generates and perceives electric signals and carries an elongated chin covered with hundreds of electroreceptor organs. That species is not the Lower Congo's flagship oddity, in the same way Lamprologus lethops is, but it helps explain the broader sensory world from which many Congo basin fishes come. When visibility is unreliable, another system becomes valuable. Instead of relying only on sight, these fish probe nearby space electrically. They sense objects, communicate and orient in conditions where a visually centered animal would be operating at a disadvantage. This is exactly the sort of solution you would expect from a basin full of murky channels, nocturnal movement, vegetation, and hidden structure. A river can be dark without being cave dark. It only needs to make seeing less dependable often enough for another sense to become worth the investment. Taken together, these animals start to make the Lower Congo feel less like one ecosystem and more like a set of overlapping tests. There are fish built to stay close to rock in fierce water, fish whose lineages split apart because rapids function as barriers over distances as small as 1.5 kilometers. Fish whose bodies suggest deep, low-light, high-pressure habitats. Fish that rely on electrolocation in dark and turbid conditions. AMNH researchers have been blunt about the scale of this diversity, calling the Lower Congo one of the most biologically diverse rivers in the world and describing its fish evolution as extraordinary. The reason is not just the number of species, although that number is impressive enough, it is the density of specialization. The Lower Congo keeps producing forms that look as though they were shaped by a fine-toothed set of local filters. This current here, that canyon there, one protected margin, one violent crossing, one hidden trough, one stretch of rock that can be occupied if your body is built correctly. Over time, the fish become little summaries of those conditions. The timescale matters as well. The lower Congo cichlid radiations studied by Schwarzer and colleagues appear to line up with the establishment of modern lower Congo habitat availability over the last roughly 5 million years, and a more recent AMNH summary says some endemic lamprologian species, including the blind L. lethops, likely emerged during dry periods in the early to middle Pleistocene when lower discharge isolated populations into smaller pockets of water. That means the creatures in this hidden realm are not just products of present-day hydraulics, they are also records of changing river history. When discharge dropped, habitats fragmented differently. When flow patterns changed, populations were trapped in new ways. When deep habitats became more or less available, some lineages took paths their relatives did not. So the bodies we are looking at now are not simply reactions to one static river. They are reactions to a river that has shifted over time while preserving its talent for separation. That helps explain why the lower Congo is so hard to discuss without sounding slightly amazed. In many famous rivers, diversity comes from size, tributaries, floodplain complexity, or old basin history spread across huge distances. The lower Congo does have those broader basin advantages behind it, but in this short and violent stretch, there is also something more concentrated at work. The river is making isolation happen at unusually fine scales. It is creating what one AMNH piece calls hotspots of species diversity in rapids, with geographic separation acting through water rather than through obvious land barriers. Once that becomes the main pattern, the creatures start looking less eccentric and more logical. A blind, depigmented cichlid is the logic of depth and low light. A reduced swim bladder cichlid is the logic of exposed rock and force. An electric fish with a sensor-packed chin is the logic of murk and close-range navigation. The hidden realm is not full of random oddities. It is full of fitted answers, and that is probably the most unsettling part. These creatures are not fringe accidents clinging to the edge of a normal river. They are exactly what this river tends to produce. The lower Congo has had enough time, enough force, enough compartmentalization, and enough hidden structure to shape lineages that make perfect sense once you accept the river on its own terms. The animals are telling us that the hidden realm is real, because they are carrying its rules in their anatomy. Some are known from tiny ranges. Some are known from very few specimens. Some are still being sorted out genetically and biogeographically. But even with that uncertainty, the message is already clear. We do not understand the river first and then explain the creatures. Very often, the creatures are how we realise what the river has been doing all along. Their eyes, bodies, buoyancy, sensory systems and distributions are clues left behind by hydraulics, too complex to see directly. Which is also why, once you start paying attention to them, the next problem becomes impossible to ignore. A river that can build animals this specialised is almost guaranteed to be hiding structure that still has not been fully mapped. At this point, it becomes tempting to ask a very modern sort of question. Surely a river this famous, this large, this scientifically important, must be fully mapped by now. We have satellites, we have sonar, we have GPS, we have instruments that can measure height from space and current from a boat, and rainfall from orbit. So how can so much of the Congo still resist a complete, confident map? The answer begins with a small but useful correction. The outline of the Congo is mapped. Its existence is not the mystery. The hard part is everything that people casually bundle into the word map without noticing. Depth, bed shape, velocity structure, seasonal change, floodplain connectivity, water hidden beneath forest canopy, discharge, changing channel slopes, the true geometry of the places where a wide surface disguises a complicated interior. When scientists say the Congo remains poorly mapped, they do not mean nobody can find it. They mean the river is still withholding the level of detail needed to make it behave like a solved system. That matters because a good river map is not just a blue line and a few labels. For a river like the Congo, mapping means understanding how the channel floor changes over long distances, where the water surface slope steepens or flattens, how much water is moving, which channels are active at different times of year, where wetlands connect or disconnect, and how floodwaters spread through forested terrain that is often very difficult to observe directly. The 2019 Congo Field Campaign made this plain. The authors combined field measurements of water surface elevation, depth, velocity, and discharge with satellite observations, and they still emphasize that satellites cannot directly measure bathymetry or discharge. In other words, even a modern view from above does not automatically give you the things a hydrologist most wants to know. It gives clues. It does not hand over the whole mechanism. The first reason so much remains incompletely mapped is brutally simple. The observation network thinned out. A major 2023 review of African water monitoring describes the Congo Basin as a striking example of hydrological decline in ground-based observation. Until the end of the 1960s, more than 400 gauging sites in the basin were providing water level and discharge observations. Today, only about 15 gauges are considered operational. The same review notes that ground-based hydrological information has dramatically decreased over recent decades across Africa, and that restricted public access to existing data can further limit scientific use. Another review on African hydrometeorological monitoring ties this deterioration to underfunding, and in some cases military conflict. That means scientists trying to map the Congo today are not building on a dense, healthy, openly shared network. They are often trying to reconstruct a giant river system after many of the regular measuring points went quiet. A map made with too few fixed reference points becomes less a finished portrait and more a set of increasingly educated guesses. And that loss is more serious in the Congo than it might be elsewhere because the basin is so large and so internally varied. The same review notes that in situ networks are especially sparse in remote areas with difficult access or security concerns. The Congo is full of exactly those difficulties. The river basin extends across immense areas of forest, wetlands, floodplains, multi-channel reaches, and remote interior landscapes where field campaigns are expensive and slow. Large rivers are already awkward to monitor consistently. Large rivers running through dense tropical terrain are worse. Large rivers running through dense tropical terrain after decades of declining gauge coverage become the sort of systems that keep hydrologists humble. If you cannot maintain enough stations on the ground, every other method has to carry more weight than it was originally designed to bear. Then there is the second problem, which is that the river is physically unfriendly to the act of being measured. In the lower Congo, USGS researchers found one of the deepest, most energetic river reaches on Earth, with turbulent and secondary flow structures spanning the full depth of the channel, in places up to 165 metres, and with depth average velocities in high shear zones exceeding 4 metres per second. Their fieldwork required local boats and operators because of the remoteness of the survey sites and the lack of navigable water, and even then they reported that swift, turbulent flow made it difficult to hold repeated transects. Large vortices, 3 to 4 metres in diameter, could open beneath the pirogue and disrupt the intended line. That is a deeply annoying way for a river to behave when your entire method depends on crossing it in a controlled pattern. Mapping sounds tidy until the water starts moving the platform carrying the map. This is why can it not be mapped, is really a question about repeated precision. A single pass through difficult water can tell you something. A map worthy of confidence usually demands many good passes, clean positioning, reliable direction, corrected velocities, and a reasonable ability to compare one survey to another. The lower Congo pushes back on each of those requirements. The 2009 USGS work notes that field conditions, river conditions, time, and logistics made it difficult to adhere completely to standard ADCP discharge protocols. Their recommendations for future work were revealing: better echo sounding, more experienced operators in that environment, improved compass reliability, more transects with navigation software, and more accurate differential GPS. That is not the language of failure. It is the language of a river that makes every ordinary step in the measurement chain harder than usual. If the platform drifts, if the current changes with depth, if the bed drops sharply, if the line is hard to repeat, the resulting map becomes partial by necessity. The third problem is that the Congo often defeats the easy assumption that a large river should be easy to see from space. It is large, yes, but the information scientists need is not always sitting in the visible part. The 2019 Geophysical Research Letter study found that along one 150-kilometre reach of the Middle Congo, Envisat-derived water surface profiles overestimated water surface elevation by as much as 2 metres because of insufficient spatial coverage. The authors note that these errors could propagate through hydraulic models and affect inundation predictions, and they calculate that in one reach this translated to a discharge difference of about 8,300 cubic metres per second, or 37%, relative to measured flow. That is not a rounding error. That is the sort of miss that can make a model tell a comforting story while the river is doing something else. So even where satellites help enormously, the Congo still finds ways to exploit the gaps between their tracks and the assumptions built into their retrievals. The really strange part is that this happened on one of the world's largest rivers, in a reach that is hydraulically subcritical rather than wildly steep. The same 2019 study says these findings were unexpected for a river of this size and show that higher resolution remote measurements are needed to capture water surface slope variability adequately. The lesson is not that satellite altimetry is useless. It is that a giant river can still vary at spatial scales coarse satellite coverage fails to resolve. That is almost rude, really. Most people assume size makes detection easier. The Congo agrees only up to a point. It is big enough to be seen, but still structured enough to hide important changes between the places where instruments happen to look. That brings us to the fourth reason, and this one is almost unfair. Much of the basin is covered by dense forest, and that forest interferes with observation in several different ways at once. The 2019 Congo field paper states directly that dense forestry over much of the basin makes inundation extents difficult to observe and topographic data subject to large uncertainties. The broader African Monitoring Review says measuring the distribution and variability of surface waters has always faced major difficulties, especially on the ground in large floodplains and wetlands, under vegetation, or during inundation events. Optical and infrared sensors can offer good spatial and temporal resolution, but in tropical Africa their usefulness is limited by dense clouds and vegetation. That means the basin often asks science to monitor water hidden by forest under a ski that is not reliably cooperative. The river does not merely occupy difficult terrain, it occupies terrain that can hide its wettest behaviour beneath trees and cloud. And the Congo's floodplains are not small side notes. They're extensive, seasonally dynamic, and in places deeply entangled with forest. This same review explains that satellite methods have improved understanding of the Congo's rivers and wetlands, but it also says that topography in floodplains and flooded forests remains poorly known at fine spatiotemporal resolution. That is a very practical obstacle. If you do not know the fine topography well enough, it becomes harder to model where water will spread when wetlands connect, how backwater effects move through the system, and how different parts of the floodplain exchange water with the main channel. A floodplain under forest canopy can behave like a half-hidden extension of the river. You know it is there, you know it matters, but the map remains blurrier than you would like because the landscape keeps too much of itself under cover. Radar and microwave methods do help, but they arrive with their own compromises. The same review notes that passive microwave observations are not limited by cloud cover and can even retrieve some water under dense canopy, which has allowed products such as SMOS-based mapping to characterize Congo Basin water body variability. But those products often work at coarse spatial resolution, around 10 to 50 kilometers, and may therefore miss smaller water bodies or finer scale structure. The review also says a recent product mapped Congo Basin water body variability at about 50-kilometre spatial resolution and weekly temporal resolution, useful for basin-scale patterns, but obviously not for the detailed mapping of a narrow channel, a hidden side connection, or a local hydraulic threshold. It is a bit like trying to understand city traffic using a weather map. You can see the big pattern. You cannot tell who is parked badly near the corner. Synthetic aperture radar gives sharper views, and the review says JERS, 1ALOS/PALSAR, were used to derive seasonal flooding dynamics and vegetation types in parts of the Congo Basin. But there is a catch there too. JERS-1S AR mosaics served reasonably well for appraising maximum flood extents, yet performed poorly in assessing dynamics and the range of variation. High-resolution SAR observations are powerful, but the review notes that they can involve large data volumes and low temporal frequency, limiting systematic long-term inundation assessments across the basin. So there is no simple rescue here where one sensor sweeps in, clears the clouds, peeks under the trees, catches every seasonal change, and hands over a perfect moving map. Instead, each technology solves one piece while leaving another slightly irritated and unresolved. Then there is the fifth reason, which is that the Congo is not just one channel. In many reaches it is multi-threaded, wetlands are connected in complicated ways, and flood behaviour differs from what scientists see in more frequently studied systems such as the Amazon. The African Monitoring Review cites work showing that the Congo system has less connectivity between the main channel, floodplains, and interfluvial areas than the Amazon. That sounds technical, but it matters enormously for mapping because it means water is not simply spilling in and out of the floodplain in an obvious regular pattern. Some parts connect weekly, some connect seasonally, some stay semi-isolated for long periods. A basin with less obvious connectivity is harder to model because the pathways of exchange are more selective and often less visible. The water moves, but not always through the routes an outsider would expect. The same review points out that modelling over the Middle Congo often had to rely on satellite-derived surface water elevation and extent datasets because dense rainforest prevented routine acquisition of higher resolution flood extents from ordinary satellite imagery. That is an important admission. Even when scientists build basin-scale hydraulic models, they are still working around observational gaps created by the rainforest itself. The models are not useless, they're often impressive, but a model built partly because the terrain blocks more direct observation carries that limitation forward. It can estimate, it can infer, it can integrate different data sources. What it cannot do is turn an observationally stubborn environment into an easy one by force of good intentions. There is also a sixth reason, and it sounds almost too obvious until you remember how much trouble it causes. Time matters. Rivers are not statues. The Congo changes by season, by discharge, by flood wave, by the state of wetlands and tributaries, and by the changing relationship between channel depth and channel width. The 2019 field campaign showed significant shifts in water surface slope and hydraulic behaviour along the Middle Congo, including marked changes near the outlet of the Cuvette Centrale. The authors argued that capturing such spatial variability is important for hydraulic characterisation and flood modelling. A single survey cannot solve that permanently. Even a very good map risks becoming incomplete the moment the water regime changes. The Congo is large enough and slow in some places, fast in others, and connected to enough wetland storage that time itself becomes part of the mapping problem. You're not only trying to map where the water is, you're trying to map how it behaves through time in a basin that does not offer dense continuous observation, and so the phrase "still cannot be mapped" turns out to mean something more precise and less mystical. The Congo can be mapped in pieces, in campaigns, in reaches, in seasonal products, in altimetry records, in hydraulic models, in sonar transects, in wetland classifications, in floodplain approximations, and in virtual stations built from many satellite missions. In fact, the African Monitoring Review notes that more than 2,000 virtual stations are now available in the basin thanks to multi-mission altimetry. That is real progress. It has revealed seasonal dynamics, annual flood pulses, and important basin-scale variability. Yet the same review also says that water levels and slopes at fine spatiotemporal resolution remain very limited, that topography in floodplains and flooded forests is still insufficiently known, and that river discharge is still not properly measured from space. In other words, the map is getting better, while the hard parts remain stubbornly hard. Progress is real. Completion is another matter. That is probably the most honest way to say it. The Congo is not a blank on the page. It is a river where the remaining blanks sit exactly in the places that matter most for understanding force, risk, habitat, and change. The easy parts were always going to yield first: the outline, the broad course, the major tributaries, the basin scale. What remains difficult are the hidden pieces: the bed under violent water, the floodplain beneath dense forest. The exact slope changes between sparse satellite tracks, the local channel form that turns one reach into a barrier and another into a refuge, the dynamic connection between main stem, wetland and side channel through the year. These are not decorative details. They are the details that decide whether a map behaves like knowledge or just a very confident sketch. So the real answer is not that the Congo has somehow escaped all modern science. It is that this river keeps forcing science to work in fragments and then stitch those fragments together carefully. Too few gauges, too much forest, too many clouds, too many wetlands, too much dangerous water in the lower reaches, too much hidden relief, too much seasonal change, too much reliance on instruments that each solve one problem while leaving another half solved. It is a river large enough to be famous and complicated enough to remain unfinished in the ledger, and that unfinished quality has consequences, because once maps begin thinning out, so does certainty. That is usually when people stop sounding authoritative, start sounding cautious, and discover that the line between exploration and risk has been much closer than they thought. Certainty is one of the first things the Congo takes away, not in a magical sense, and not because the river enjoys being dramatic. It happens in a much more practical way. A person arrives with a map, a theory, a route, a schedule, a boat, a notebook, a confident tone, and the river begins trimming those things down to size. That pattern is old. It shows up in exploration history, in transport history, in literature, and in modern field science. The names and tools change. The loss of confidence does not. The lower Congo especially has a long habit of making people feel that they understand the situation right up until the water demonstrates that understanding and control are not the same thing. It is worth saying carefully that the river was never unknown to the people living with it. The story does not begin with a European stepping ashore and discovering that water had been there all along, which is a very flattering version of history for the wrong people. Britannica's account of the Congo's study and exploration notes that Portuguese navigator Diogo Cao encountered the river's mouth in 1482, and that long before Henry Morton Stanley arrived in 1877, some 17th century Capuchin missionaries had likely reached the shores of Malibbo Pool. That tells you two things at once. First, outside knowledge of the river by Europeans came in fragments. Second, even those fragments were late arrivals to a waterway that was already central to the lives of river communities. The lower Congo did not wait around in blank silence until someone from abroad decided it was important. And yet, once outsiders tried to turn the Congo into a solved route, the trouble began almost immediately. The problem was never simply finding the river. The problem was getting through the lower course, and doing so with enough confidence to treat the river as a corridor rather than a barrier. Britannica notes that James Kingston Tuckey's 1816 British Admiralty expedition was amply supplied, yet it was decimated and had to retrace its steps before surmounting the cataracts. That is one of those historical details that sounds polite until you think about what it means. They did not fail because the river was absent, vague or small. They failed because a river can be very present and still refuse passage. The certainty they brought with them did not survive contact with the lower course. That lower course is the key to nearly every story of frustration that follows. Livingstone Falls is not a single waterfall, but a long series of 32 rapids and cataracts stretching about 220 miles, or 354 kilometres, between Kinshasa and Matadi, with a total drop of roughly 850 feet, or 260 metres. Britannica states plainly that these falls prevent navigation from the river mouth to the interior. Another Britannica overview puts the point even more bluntly. The cataracts render the Congo unnavigable between Matadi and Malibbo Pool. This is one of the most revealing facts about the whole system. The Congo forms Africa's largest network of navigable waterways, and then, in the lower course, becomes the obstacle that breaks that continuity. A river that huge should feel like access. Instead, in its most famous stretch, it behaves like interruption. So when Henry Morton Stanley crossed the falls in 1877 and charted the course of the Congo, the accomplishment mattered, but it did not magically turn the river into a tame piece of infrastructure. Britannica records that he crossed the falls in that year, and the same exploration summary makes clear that the lower Congo had already broken earlier ambitions. Stanley added knowledge. He did not cancel the river's terms. That distinction matters because the story of exploration is often told as if once the route is charted, uncertainty is basically over and only logistics remain. The lower Congo is a useful correction. Charting the course is not the same as neutralizing the hazard. You can know where the obstacle is and still be blocked by it. A map can reduce ignorance without reducing force. That is why the river ended up needing to be bypassed rather than simply mastered. Britannica's account of the Congo's economic history says that before inland development could proceed at scale, it was necessary to overcome the barrier to the sea formed by the lower course, and that this was accomplished not by making the river navigable through the cataracts but by building railways. The line between Matadi and Leopoldville, now Kinshasa, opened in 1898, and the Congo Ocean line between Brazzaville and Pointe-Noire was completed in 1934. That is a revealing kind of surrender. Not a total surrender perhaps, but an admission. The solution to the lower Congo was not to insist harder that boats should go through. The solution was to step aside and move goods around the river's most stubborn section. When transport planners start laying track to get past the water has made its point. This is also where wrecks become more than a simple image of broken wood and overturned boats. Wrecks, in the Congo story, are often wrecked plans, wrecked assumptions, wrecked schedules, wrecked notions that a continuous river must be continuously usable. Of course, the physical danger is real as well. A.M.N. Actions Field, reporting on the lower Congo, describes large whirlpools and parcels of water rising from the depth strongly enough to capsize small boats. USGS fieldwork adds that large vortices could open beneath a pirogue and make it difficult to maintain a planned course, while high velocities made shore-to-shore navigation a challenge, so the wreckage is literal enough when required. But what the river destroys most consistently is confidence. The boat can still be floating while the certainty inside it has already gone under. That loss of certainty has a very particular rhythm to it. First, the river looks broad enough, visible enough, established enough. Then the lower course tightens, accelerates, and begins putting all the hidden terms back into the conversation. The 2008 USGS survey paper notes that the lower Congo drops about 280 metres in 350 kilometres between Kinshasa and the Atlantic, and that the first 130 kilometres below Malibbo Pool contain a series of extreme rapids that no one had successfully descended and documented until 2008. Think about that for a second. This was not an obscure creek in an unvisited valley. This was one of the world's great rivers, and a major lower section of its extreme rapids had still not been successfully descended and documented until the 21st century. That is not a failure of interest. That is a measure of difficulty. and even when modern teams did go in, certainty still vanished in a very old-fashioned way. The tools were newer, the feeling was familiar. US, GS and A, MNH, teams using acoustic Doppler current profilers, GPS and echo sounders found a river that remained difficult to cross in controlled transects. The survey relied on local boats and operators because of the remoteness of the sites and the lack of navigable water. In some places, vortices 3 to 4 meters in diameter opened under the pirogue. The same work found dramatic bed changes, localized jets, and depth average velocities above 4 meters per second in high shear zones. This is a useful reminder that certainty does not disappear only in the era of hand-drawn maps and exhausted expeditions. It disappears whenever the river's actual structure becomes stronger than the method being used to simplify it. There is another reason this chapter in the story lingers so strongly in people's minds, and that is literature. Britannica notes that to the literary-minded, the Congo is evocative of Joseph Conrad's 1902 Heart of Darkness, a work that conjured an atmosphere of foreboding, treachery, greed and exploitation. Conrad himself spent 4 months in the Congo in 1890 and returned to England in January 1891, with Britannica stating that what he saw, did and felt there is largely recorded in that story, and that his Congo experience was deeply traumatic. This matters, but not in the lazy way people sometimes handle it. Conrad did not invent the river's unease from nothing. He attached literary language to a place already tangled with physical difficulty, colonial violence, and moral collapse. The atmosphere stuck because the instability was real, even if the book then amplified it into something broader and darker. That said, it helps to separate two different things. The Lower Congo did not become frightening because a novelist found it useful. It became useful to a novelist because so much around it was already unstable. The cataracts were real. The transport barrier was real. The logistical difficulty was real. The colonial exploitation Conrad encountered in the Congo Free State was real enough that Britannica describes the state in 1889 as already notorious as a sphere of imperialistic exploitation. So when certainty vanishes in the Congo story, it is not only because the water is dangerous, it is because the human systems around the water have often been exploitative, extractive, and unreliable as well. The river becomes the setting where physical hazard and moral hazard meet, which is one reason it leaves such a deep mark in memory. There is also something very revealing in the difference between how the middle and lower river behave in human imagination. The Middle Congo supports long navigable routes and is essential to transportation in regions where roads are limited. Britannica describes some 8,700 miles of navigable waterway within the Democratic Republic of the Congo alone, even if actual commercial traffic remains below potential and the system has suffered from aging infrastructure and lack of maintenance. That broad inland network encourages a certain confidence. It makes the Congo sound like a giant route, and in many ways it is, but the lower course then interrupts that confidence with the exact sort of section that forces planners, traders, scientists and travellers to stop using one word for the whole river. A giant route becomes, in one reach, a giant refusal. Certainty vanishes because the river changes function without changing name. Scientists have felt the same pattern in their own way. The Lower Congo is one of the deepest, most powerful, and most biologically diverse river stretches on Earth, yet USGS researchers say much of it remains a mystery from a hydraulics perspective. Their velocity mapping work describes a bedrock-controlled reach where full-depth, turbulent and secondary flow structures can span up to 165 meters, and where coherent bank-to-bank cross-channel flow structures are absent. That sounds technical, and it is, but emotionally it is another episode of vanishing certainty. The river is there, the instruments are there, the team is there. Yet a system this energetic still refuses to flatten into a simple pattern. Instead of one readable cross-section, the researchers find isolation zones, high shear barriers, and flow behaviour that undermines easy assumptions about connection. Even expert measurement has to proceed with caution, because the water remains more complicated than the broad category river suggests. In that sense, the modern scientist and the 19th century explorer are not doing the same work, but they are learning a related lesson. The old expeditions lost certainty through route failure, illness, cataracts, and the simple fact of being stopped. The modern teams lose certainty more quietly. A transect drifts. A current profile turns out stranger than expected. A satellite pass misses an important slope change. A gauge record is absent because the station was abandoned long ago. A fish population that appears nearby on a map is genetically isolated because the water between the two groups functions as a wall. The form of ignorance changes. The feeling behind it remains recognisable. The Congo is not one of those places where technology erased humility. It is one of those places where technology made humility more precise. That is why stories of the river so often drift toward caution, even when the speaker is trying to remain matter of fact. AMNHE's reporting on the Lower Congo mentions small boats being easily capsized by whirlpools and notes that the river remains unruly and unpredictable for about 350 kilometres before reaching the Atlantic. USGS Public Outreach on the 2008 expedition asks listeners to imagine a dugout canoe crossing rapids and whirlpools while measuring depths of over 700 feet. These are not myth-making details. They are field conditions. They give the Lower Congo a reputation that feels old because it has been earned repeatedly in different eras and by different kinds of witnesses. Explorers found it obstructive. Transport networks found it non-negotiable. Writers found it morally loaded. Hydrologists found it technically resistant. Biologists found it full of separations hidden inside the water. Certainty keeps arriving from a different angle and leaving by the same door. And there is one more reason the certainty vanishes so thoroughly here. The Lower Congo does not merely defeat the casual observer, it also punishes the assumption that once an environment is famous, it must therefore be well understood. Fame and knowledge are not the same thing. The Congo is famous enough to sit in school books, in colonial archives, in travel writing, in literature, and in public imagination. Yet the USGS measurement paper from 2009 still says there was little basic hydrologic and hydraulic data available for the Lower Congo, despite its geologic, geomorphic, biologic, and economic significance. That sentence alone explains a great deal. People can talk about a place for centuries and still fail to know it in the ways that matter most. A famous river can remain underdescribed exactly where it is most forceful. Perhaps that is why the wrecks in this story feel larger than its timber and metal. The Lower Congo keeps wrecking shortcuts. It wrecks the shortcut that says a charted route is a solved route. It wrecks the shortcut that says a navigable basin must be navigable all the way to the sea. It wrecks the shortcut that says a mighty river should be easy to monitor because it is impossible to miss. It wrecks the shortcut that says literature exaggerated everything beyond recognition. It even wrecks the shortcut that says modern science has arrived too late to be surprised. The river has been demonstrating the opposite for centuries. What vanishes here is not just certainty about what lies ahead, it is certainty about what category the place belongs to at all. Transport artery, exploration route, hydraulic barrier, evolutionary engine, colonial corridor, scientific puzzle. The Lower Congo keeps being all of them at once, which is not a kind arrangement for the human mind. So when people talk about explorers, wrecks, and vanishing certainty, they are really talking about a long record of the same correction. Someone believes the river can be reduced to a route, a story, a model, a plan, or a measurement. Then the river gives back a narrower answer. No, not like that. Not here. Not with those assumptions. Not at that speed. The Lower Congo has done this to expeditions, to transport schemes, to literary imagination, and to scientific fieldwork. It does not reject knowledge. It rejects easy knowledge. That distinction matters because it brings us to the most useful question the river leaves behind. If the Congo keeps stripping away lazy certainty without becoming unknowable, then what exactly is it still teaching the people patient enough to keep measuring, comparing, and listening? What the Congo is still teaching science is not one neat lesson that can be framed and hung on a wall. It is more irritating and therefore more useful than that. The river keeps teaching that large natural systems do not become simple just because they are famous, mapped in outline, or observed from space. It keeps teaching that size can hide detail instead of revealing it. It keeps teaching that a river can be both a transport route and a barrier, both a freshwater habitat and part of a deep-sea sediment system, both a local necessity and a global scientific case study. And perhaps most importantly, it keeps teaching that the old habit of treating rivers as obvious connectors is often too simple. In the lower Congo, water is not merely what joins places, it is also what divides them, isolates them, and forces them into new forms. That alone has changed the way many researchers think about river systems. For a long time, the most glamorous stories in evolution came from islands and lakes. Islands make sense to people. You can see the border. Lakes make sense too. They are bounded, enclosed, and easy to imagine as separate worlds. Rivers were often treated as the opposite, as threads of movement, corridors through which fish, nutrients, and populations could spread. The lower Congo has been steadily correcting that picture. Genetic studies in lower Congo cichlids showed unusually strong isolation over short distances, and later, genome-wide work added a more nuanced result. Powerful rapids can act as barriers to gene flow, but at some scales they may also allow multi-directional dispersal opportunities. That is a very grown-up kind of scientific answer. Not a cartoon wall, not a free-for-all corridor, but a dynamic riverscape in which movement depends on scale, species, and time. Science likes systems that pick one behaviour and stick with it. The Congo keeps answering, no, it depends, which is one of the least satisfying and most honest things nature ever says. That matters beyond fish. Once a river is understood as an internal landscape rather than a single connected tube of water, a great many assumptions have to be revised. The 2011 work on lower Congo cichlid colonization argued that a high level of riverine diversity originated in the lower Congo within about 5 million years, in step with the development of the modern lower Congo rapids, and that widely distributed lineages show a spatial genetic structure matching a trisection of the river into major biogeographic areas. In other words, the river is not only shaping populations in passing, it has become part of the long-term mechanism by which diversity is generated. That gives science something extremely valuable, a riverine system that can be used as a model for speciation, not just a scenic backdrop for it. Lakes had that prestige for years. The Congo is forcing rivers into that conversation much more seriously. The river is also teaching hydrology to stop pretending that the visible surface is the whole story. Field campaigns and hydraulic measurements in the lower Congo found full-depth turbulent and secondary flow structures, high shear zones, strong vertical exchange, and bedrock-controlled channels with dramatic bathymetric changes. Meanwhile, fieldwork on the Middle Congo showed greater water surface variability than satellite products alone had captured, including important slope changes along reaches where coarse coverage missed key behaviour. Taken together, those results teach a simple but expensive lesson. A big river can look legible from above while still hiding crucial mechanics below. The surface tells part of the truth. The river floor, the submerged geometry, and the internal velocity field tell the rest. That is not just a Congo lesson. That is a lesson for how scientists approach other data-poor large rivers, where the temptation to trust remote sensing a little too quickly is always present. It has also been teaching scientists how to combine methods rather than worship any one of them. The older fantasy in environmental science was often that one new tool would solve the hard part. Satellites would solve access. Acoustic instruments would solve depth. Modelling would solve missing observations. Genetics would solve hidden structure. The Congo has been steadily discouraging that fantasy. The 2022 HESS synthesis on surface hydrology in the basin relies on in situ observations, radar altimetry, and multi-satellite surface water extent together, explicitly because the basin remains relatively poorly known, and because no single method can capture the full system on its own. The 2023 review of freshwater resources in the basin makes the same point from another angle. Ground data are sparse, satellite observations have improved the picture, and even missions like GRACE still miss important parts of total drainable water storage. The real lesson here is methodological humility. The Congo rewards patchwork science, cross-checking and layered evidence. It punishes the hope that one clean dataset will be enough. And then there is the issue of monitoring, which the river has turned into a much larger scientific and institutional lesson. The basin used to be far better gauged than it is now. Reviews of African surface water monitoring note that until the end of the 1960s, more than 400 gauging sites provided water level and discharge observations in the Congo basin, whereas today only about 15 gauges are considered operational. That decline has consequences well beyond paperwork. It means the river is teaching science that infrastructure is part of knowledge. A brilliant model cannot replace a gauge that was never maintained. A beautiful satellite product cannot fully substitute for long local records that do not exist or are inaccessible. Science sometimes likes to speak as though ideas float above institutions. The Congo has a less flattering message. Without durable monitoring networks, trained local experts, data access and long-term maintenance, even one of Earth's greatest rivers can remain underdescribed in ways that affect forecasting, navigation, ecology, and policy. That is why one of the most important things the Congo is teaching right now has less to do with the river itself than with who gets to study it and how. The Royal Society's Congo River hydraulics and morphology work describes the basin as one of the least studied regions in the world after decades of war, and says that up-to-date scientific knowledge of channels and wetlands is vital for reconstruction and climate resilience. The 2024 CRUHM project summary goes further, noting that the project examined the outcomes of a 6-year effort that carried out the first large-scale scientific expeditions to the basin of the modern era, and that part of its legacy was establishing a new hydrology research centre at the University of Kinshasa, while building a wider community of Congo Basin researchers. That is not a side note, it is one of the clearest lessons of all. The river is teaching that science in the Congo cannot be a recurring fly-in performance by outsiders with equipment. It has to become durable, local, trained and continuous, or the data gaps simply reopen as soon as the expedition leaves. There is another scientific lesson that would have sounded almost unrelated a generation ago. The Congo is teaching that rivers and oceans should not be treated as separate chapters, with a clean break at the coast. Work published in Nature Communications showed that turbidity currents originating from the Congo River mouth travelled more than 1,130 kilometres through the submarine Congo Canyon and Channel, while accelerating from 5.2 to 8.0 metres per second. The study found that in 1 year these flows eroded 1,338 to 2,675 million tonnes of sediment from one submarine canyon, and showed that river floods, sometimes helped by spring tides after a delay, can generate canyon flushing flows. That means the Congo is not just teaching hydrology, it is teaching land to ocean continuity in a very forceful way. The river does not stop being important when it reaches salt water. It keeps moving sediment, carbon and geomorphic change far offshore. A river lesson becomes an oceanographic lesson almost immediately. The carbon story adds another layer. The 2022 AGU chapter on Congo Basin hydrology, climate and biogeochemistry notes that the Amazon and the Congo together account for about a quarter of global river discharge to the oceans, and that the emerging Congo dataset is allowing scientists to think more generally about how the world's largest tropical rivers function in the global carbon cycle. The same chapter describes the Congo as a highly dynamic region of aquatic carbon cycling, with substantial dissolved and particulate organic carbon export, and with the Congo Canyon facilitating burial of particulate organic carbon to the abyssal plain. That means the river is teaching science that tropical basins are not just pipes moving fresh water to sea. They are active biochemical systems that process, store, emit and export carbon in ways that matter globally. For a long time, the Amazon monopolized a lot of that attention. The Congo has been forcing a broader comparison, and that comparison is making the science itself less lopsided. The basin has also become a classroom for climate-linked hydrology. A 2023 Congo reanalysis study modelled daily discharge from 1981 to 2020 and examined major floods and droughts together with ENSO teleconnections. The authors found that severe droughts in 1983 to 1984 and 2011 to 2012 were strongly correlated with preceding El Niño and La Niña conditions, while the 1997 to 1998 flood in the south and central basin was statistically linked to a major El Niño event, though the 2019 to 2020 flood did not fit that same simple relationship. That may sound like a specialised modelling result, but it teaches something broader. The Congo is not a system where one climate lever always pulls one hydrological response. There are teleconnections, lags, wetland storage effects, lake dynamics, and regional differences inside the basin. Once again, the river resists the neat version of the story. Science goes in hoping for one master switch. The Congo replies with interacting controls and delayed consequences. Even the basin's apparent lack of complete visibility has become a useful teacher. The 2022 HESS study used 2,311 radar altimetry virtual stations, together with historical and contemporary in situ observations to better characterise surface hydrology, including the basin's annual flood dynamics and its unusual bimodal pattern. That is progress of a very real kind. At the same time, the larger reviews keep emphasising that the Congo remains relatively poorly known, and that fine-scale surface water slopes, floodplain topography under forests, and some storage dynamics are still hard to resolve. So the lesson is not that science is failing. The lesson is that progress in a basin like this is incremental, composite, and often indirect. The Congo teaches patience. It teaches that a major advance may look like a better constrained slope field, a validated set of virtual stations, or a more accurate estimate of flood timing rather than one dramatic announcement that the whole basin has finally been solved. For people who like a triumphant reveal, this is disappointing. For actual science, it is healthier. Then there is the lesson coming from the animals themselves, which may be the strangest of all because it blurs the line between biology and hydrology. The blind cichlid and other specialised lower Congo fishes have shown that bodies can preserve information about conditions instruments barely sample. Earlier work established strong genetic isolation in lower Congo cichlids, and later genomic work on multiple endemic fishes found that rapids can act as barriers, while still permitting some multi-directional movement depending on the riverscape and the timescale involved. That is a remarkable teaching tool. The river shows that ecology, flow, and evolution are not separate departments filing papers in neighbouring offices. They are entangled. A hydraulic boundary becomes an evolutionary boundary. A deep, dark habitat becomes a sensory and anatomical problem. A sequence of rapids becomes a long-term experiment in dispersal and isolation. The Congo is still teaching science to treat living organisms not merely as passengers in a river system, but as records of the river's hidden structure. There is a more uncomfortable lesson as well, and it concerns scale. Researchers often speak about large rivers as though that category alone should give them a fairly standard set of expectations. The Congo keeps showing that large rivers are not interchangeable. The basin differs from the Amazon in floodplain exchange, sediment character, organic matter transport and monitoring history. The AGU chapter notes that the Congo's waters are relatively low in suspended sediment, compared with the Amazon, yet are unusually organic rich, while the Congo Canyon makes preservation and burial pathways in the marine realm very different from those at the Amazon margin. That means science cannot simply use one famous tropical river as a template and tint the map a different colour. The Congo is still teaching comparative humility. Similar size does not guarantee similar behaviour. Second largest is not a personality type, and all of these lessons come together in one final correction that feels especially important now. The Congo is teaching science that uncertainty is not the same thing as ignorance. There is a lazy way of talking about understudied places that makes them sound empty, blank, or beyond meaningful understanding. The Congo has never been that. It is undermeasured in certain ways, yes. Difficult to monitor continuously, yes. Hard to model cleanly in every reach, yes. But the last 2 decades of work have also shown a river yielding real knowledge, new hydraulic measurements, new basin-scale hydrology from combined in situ and satellite observations, better reanalysis of floods and droughts, new evolutionary frameworks for riverine speciation, and stronger evidence for river-to-ocean continuity in sediment and carbon transport. So the lesson is not that the Congo defeats science. It is that it disciplines science. It forces slower claims, stronger collaboration, better methods, and more respect for the difference between outline and understanding. That is probably why researchers keep returning to it. Not because it offers easy prestige, it does not. Not because it turns quickly into neat certainty. It does not do that either. They return because the Congo remains one of those rare systems that still changes the questions being asked. It takes familiar scientific ideas about connectivity, barriers, sensing, monitoring, carbon and climate, and makes them harder, sharper, and more realistic. A river that can do that is not just an object of study. It becomes a kind of instructor, stern in manner, poor in hospitality, but unusually good at exposing weak assumptions. And once a place starts doing that consistently, it becomes very difficult to dismiss the fear surrounding it as mere drama, because by then the fear has become something much more sober. It is the recognition that the danger is not folklore, not exaggeration, and not a misunderstanding of ordinary water, but a measured response to a system whose depth, force, and hidden structure have earned their reputation piece by piece. By now, the phrase "the fear is not folklore but depth" has probably started sounding less like a dramatic line and more like a summary. That is really what it is. The Congo does not need to borrow mystery from rumour. It does not need invented monsters, whispered curses, or the usual nervous habit humans have of dressing ordinary danger in supernatural clothes. The river is perfectly capable of unsettling people on its own merits. It is one of the deepest rivers on Earth, with measured depths in excess of 220 metres in the lower reaches. It carries an enormous volume of water, with average discharge at its mouth around 41,000 cubic metres per second. In the lower course, it drops steeply, races through rapids and cataracts, and produces high-velocity, high-shear flows that can isolate habitats and make controlled measurement difficult. Those are not campfire details. Those are hydrological facts. And once you have enough of those facts in one place, fear stops being superstition and starts looking like a reasonable response to a river that does not behave the way most rivers do. That distinction matters because folklore usually begins where explanation ends. Something is dangerous, strange, or difficult to understand, so people give it a story large enough to hold their uncertainty. The Congo has inspired plenty of narrative over the centuries, some of it literary, some colonial, some careless, some sensational. But the modern scientific picture is not moving away from fear by reducing the river to something bland and harmless. It is moving toward a more grounded form of fear. The more researchers measure the lower Congo, the more they find a system that is physically extreme in exactly the places where humans are least comfortable. In the hidden parts, the dark parts, the fast parts, the parts beneath the surface where ordinary observation fails and even careful instruments begin working under pressure. So the river becomes less mythical and more severe. In a curious way, the facts make it stranger, not simpler. Take the depth alone. A river can be large without becoming conceptually unsettling. Plenty of large rivers still fit the basic picture most people carry in their heads. Wide channel, muddy bottom, changing seasonal levels, some rapids perhaps, but still recognisably a river in the comfortable mental sense. The lower Congo strains that picture until it begins to break. In the Bulu Reach and other studied sections, researchers found deep pools, bedrock-controlled geometry, and full depth, turbulent and secondary flow structures. In some areas, the entire water column is involved in the river's movement in a way that is difficult to visualise from the bank or even from a boat. When the water is not simply flowing forward but plunging, recirculating, rising, and shearing across hidden terrain. River stops meaning what it used to mean in the listener's mind. It is still the correct word, it just no longer feels like a sufficient one, and that is really the point. The fear attached to the Congo is not based on some vague sense that deep water is spooky, though deep water has certainly been doing excellent work in human imagination for a very long time. It comes from the realization that depth in the lower Congo has consequences. It changes pressure, it reduces light, it creates habitats that seem to have shaped fish with reduced eyes and pigmentation. It allows strong vertical exchanges and upwelling zones capable of dragging material, and possibly animals, upward through parts of the water column they are not built to survive comfortably. When Lamprologus lethops appears dead or dying at the surface with signs consistent with decompression, it is not performing a ghost story for our benefit. It is delivering evidence. The river is deep enough, dark enough, and vertically dynamic enough to injure a fish simply by forcing it up too fast. That is a level of physical seriousness folklore could only imitate poorly. The current adds another layer to this. A deep river is intimidating. A deep river whose water moves with enough force to become a barrier is more than intimidating. It is conceptually disruptive. Biologists working in the lower Congo found patterns of isolation so strong that populations of fish in the same river were diverging over surprisingly short distances. AMNH and other researchers describe the rapids and strong currents as walls of water, an expression that sounds almost poetic until you realise how literal it is. If a fish cannot cross a zone of water because the flow is stronger than its ability to swim through and return, the barrier is real regardless of whether it is made of rock, ice, or violent current. This is why fear of the Congo is not about imagination running wild. It is about understanding that the river has forms of force that do the work we usually expect from land. It creates separation out of movement itself. There is something quietly unsettling about that, because it pushes against one of the oldest assumptions people make about rivers. Rivers connect. That is what they do in stories, in trade, in migration, in maps. They are lines of passage. The Congo is that too, of course. It supports one of Africa's great navigable inland systems and remains essential to transportation and daily life across the basin. But the lower Congo complicates the comforting version of that story. In some stretches, the same river that connects communities and landscapes at large scales also fragments the living world at small scales. It is corridor and barrier at once. Science tends to dislike systems that refuse a single role. Humans dislike them even more. A thing that both joins and divides is harder to file away as safe, and harder still to approach with confidence. And then there is the question of visibility. So much fear in ordinary life comes from not seeing clearly. A dark staircase, a road in fog, a sound in another room. The lower Congo operationalizes that feeling. The river can look broad and almost calm from above, yet conceal steep bed changes, deep canyons, high-velocity jets, and recirculating structures beneath the surface. Satellite observations are useful, but studies on the Congo's main stem have shown that existing altimetry can miss important changes in water surface elevation and slope, especially in reaches where spatial coverage is too sparse. Dense forest makes inundation and floodplain structure hard to observe directly. Ground gauges are far fewer than they once were. Acoustic instruments help, but even they come with blind zones near the surface and bed, and become harder to deploy cleanly in a river that tosses survey craft around, with vortices and high flow. So the river is not only dangerous, it is dangerous in a way that interferes with the very tools meant to make it legible. Fear thrives in poor visibility, and the Congo has turned poor visibility into an ecosystem, a hydrological condition and a methodological problem all at once. This is one reason scientific respect for the Congo can sound so close to alarm. It is not because researchers are unusually sentimental. It is because the river keeps forcing them to admit how much of its true structure is hidden from quick interpretation. In many natural systems, greater knowledge reduces the emotional charge. A place that seemed frightening from a distance becomes manageable once measured. The Congo does not cooperate with that comforting arc. Measurement does help, certainly. It reveals the mechanisms. It replaces speculation with depth profiles, velocity maps, genetic analyses, and basin-scale hydrology. But those mechanisms turn out to be severe enough that understanding them does not dissolve unease. It refines it. A mysterious river is one thing. A measured river that still contains 220-metre canyons, high sheer flow barriers, deep low-light habitats, and some of the most extreme rapids on Earth is another. Knowledge has not made the river ordinary. It has made the danger more precise. That is why the old stories around the Congo, however distorted some of them became, never fully detached from reality. Explorers were blocked by the lower course. Transport networks had to work around it rather than through it. Literary imagination attached itself to it because the place already carried the right mix of physical threat, opacity, and human instability. Modern science did not arrive and discover that everyone had been overreacting. Instead, it kept finding physical reasons why the river had always inspired caution. The lower Congo's cataracts and rapids remain a true barrier to navigation in that reach. The first successful documented descent of some of its extreme rapids did not happen until 2008. Field teams in pirogues recorded vortices opening beneath their boats. These are not relics of a more superstitious time. They are recurring corrections delivered by the river itself. There is also a broader lesson in that continuity. Fear becomes untrustworthy when it is detached from evidence. It becomes trustworthy when it survives better evidence. The Congo's reputation has survived contact with better instruments, better biology, better satellite data, and better hydraulic models. Not every dramatic claim people make about the river is true, of course. Human beings are very talented at embroidery. But the central instinct that there is something about this river that demands unusual caution has held up rather well. The details underneath that instinct changed. Where earlier observers might have spoken vaguely of treacherous waters, later researchers could point to bathymetry, bedrock control, secondary flow, genetic structuring, and deep habitat specialization. Yet the feeling that the river should not be underestimated remained. That persistence is meaningful. It suggests the fear was never primarily about myth. It was about repeated encounters with a physical system that keeps humbling easy assumptions. In a way, the Congo has become a test of what kind of fear we are willing to respect. Folklore fear is easy to dismiss because it can be reduced to exaggeration, ignorance, or the human love of telling stories in the dark. Measured fear is harder to wave away. It asks for no imagination beyond what the data already support. A river deeper than 220 metres in places, with violent descent through cataracts, turbulent full-depth flow structures, patchy monitoring, difficult remote observation, and fish adapted to deep low-light conditions does not need embellishment. It requires only that we stop expecting rivers to fit our comfortable categories. The fear is not that something supernatural waits below. The fear is that what waits below is entirely natural and still severe enough to defeat ordinary intuition. That may be the most interesting part of the whole story. We often think science and fear move in opposite directions, as though one replaces the other. In reality, good science often changes the texture of fear rather than eliminating it. A child fears the dark because anything might be there. A scientist fears the lower Congo in a different way because enough is known to understand what is there. Hidden channels, pressure differences, vertical flow, shear zones, incomplete maps, limited gauges, living evidence in the form of fish that look as though they came from a cave, except they came from a river. This is not the vague terror of imagination filling a blank. It is the sober discomfort of discovering that the blank is occupied by something measurable and still more extreme than expected. And perhaps that is why the Congo lingers in the mind more than so many other dangerous places. Volcanoes are spectacular but straightforward in their intent. Mountains are imposing but visible. Storms announce themselves. The lower Congo often gives only partial notice. Its surface can look wide, dark, and even calm from above. Its real violence may be arranged in hidden layers below. Its biological weirdness does not leap out until you start reading about blind cichlids, reduced swim bladders, electric sensing, and localized endemic species. Its hydrological significance expands the farther you follow it, right out through the river mouth and into deep-sea sediment flows travelling more than 1,000 kilometres through submarine canyon systems. It keeps being more than the eye first grants it permission to be. Places like that tend to stay with people, not because they are loud, but because they are quietly disproportionate. There is another reason the fear is not folklore, and it has to do with humility. Folklore often places humans at the centre of the story. We are threatened, warned, cursed, tested, or seduced by some greater force that seems strangely interested in us. The Congo does not really care about us in that way. Its danger is impersonal. It is not watching. It is not punishing. It is simply being a river whose scale, slope, bed geometry, climate context, and evolutionary consequences exceed the templates we usually bring to rivers. That impersonality is, in some ways, more unnerving than a legend. Legends flatter us by making us the point. The Congo does not bother. It will separate fish populations, humble field teams, challenge satellite products, and root sediment into the Atlantic abyss whether or not anyone happens to be there feeling dramatic about it. Fear becomes cleaner in a place like that. Less theatrical, more honest. So where does that leave us now, at the end of this long look into one of the most intimidating freshwater systems on Earth? It leaves us with a river that is not mysterious because nobody has studied it, but because studying it has revealed layer after layer of complication. A river whose fame does not equal full understanding. A river whose living inhabitants carry evidence of darkness, pressure, and hydraulic isolation in their bodies. A river whose lower reaches can still make boats struggle, models wobble, and scientists speak with unusual caution. A river that teaches the same lesson in many languages: biological, geological, hydrological, logistical. Do not confuse visibility with simplicity. Do not confuse a map with mastery. Do not confuse one continuous line of water with one continuous world. And maybe, before we fully let the river go for the night, it is worth returning to where you are, the room around you, the time where you live, the ordinary sounds near you that, I hope, now feel a little softer by comparison. Somewhere far from that room, the Congo is still moving through forest and gorge, still carrying flood pulses, still isolating pockets of life, still sending water and sediment toward the Atlantic, still keeping some of its truth under dark water, where the surface says less than people want it to say. That is a stuff to sit with. Not a legend, not a fable, not a fear borrowed from old stories, just a river so deep, forceful, and structurally strange that even now, after all the measurements and all the maps and all the explanations, it still earns the most sober kind of respect. And that respect, if we are being honest, is often only one careful step away from fear.